Can humanity ever leave the Milky Way galaxy? Tonight, we're exploring this question through the lens of distance, velocity, and gravitational binding. Our galaxy spans 100,000 light-years, with our Sun positioned about 26,000 light-years from the center, orbiting at 230 kilometers per second. The journey beyond these boundaries would require overcoming not just distance, but fundamental physical constraints that shape how objects move through the universe. We'll look at galactic structure first, establishing the scale of what we're discussing. Then we'll examine travel speeds and energy requirements, gravitational fields that extend far beyond visible boundaries, and the expansion of space that affects everything beyond our local cosmic neighborhood. Along the way, we'll clarify what remains accessible and what lies permanently beyond reach. Welcome to Sleepytime Universe, where we explore the cosmos at a pace designed for rest and reflection. We move slowly through ideas, allowing each concept time to settle. Our galaxy takes the form of a barred spiral. At its core sits a linear concentration of stars forming what astronomers call a central bar. This bar extends perhaps 27,000 light-years from end to end. Curved arms spiral outward from each terminus of this bar, creating the distinctive pattern visible in images of similar galaxies. We orbit within one of these spiral features, specifically what astronomers designate as the Orion Arm or Orion Spur. The Orion Arm represents a smaller structure compared to the galaxy's major spiral features. It sits between two larger arms, the Sagittarius Arm closer to the galactic center and the Perseus Arm farther out. Our position within this minor arm places us roughly 26,000 light-years from the galactic center, about halfway out toward the visible disk's outer edge. Stellar population estimates range from 100 billion to 400 billion suns. This wide uncertainty arises from multiple factors. Interstellar dust blocks our view of many galactic regions, particularly toward the center, where dust concentrations run highest. Additionally, distinguishing individual faint stars from star clusters at great distances requires careful analysis of limited light. The imprecision itself conveys something important about observational challenges. Even basic census taking of our own galaxy presents substantial difficulties when conducted from within its structure. Modern surveys using infrared observations penetrate dust better than visible light, revealing previously hidden stellar populations. These surveys have revised estimates upward over time as more hidden regions become observable. The uncertainty will likely narrow as observation techniques improve, but perfect counts seem unlikely given our embedded perspective and the sheer number of objects involved. Think of the galaxy's overall form as a flattened disk surrounding a central bulge. Viewed edge-on, it would show this disk structure clearly. Viewed face-on, the spiral pattern dominates. We see neither perspective directly, but rather observe from within, looking outward in all directions through the surrounding structure. At its broadest extent, the disk reaches approximately 100,000 light-years from edge to edge. Some astronomers measure slightly larger or smaller values depending on where they define the edge. The disk doesn't end abruptly, but rather fades gradually as stellar density decreases with radius. Still, 100,000 light-years serves as a useful working number for the disk's diameter. Thickness varies substantially with distance from center. The central bulge represents the thickest region, reaching perhaps 10,000 light-years above and below the galactic midplane. This bulge contains older stars in a more spherical distribution than the disk. As you move outward from the bulge into the disk proper, thickness decreases. Out here at our orbital radius, the disk narrows to roughly 1,000 light-years thick. This gradual thinning creates the flattened appearance characteristic of spiral galaxies when viewed edge-on. The thin disk contains most young stars and ongoing star formation. Gas and dust concentrate here as well, providing raw material for new stellar generations. This flattened configuration arises from rotation. As the galaxy formed, material gradually settled into a rotating disk through conservation of angular momentum. Light provides our most useful measuring tool for cosmic distances. Traveling at approximately 300,000 kilometers each second, light covers what we term a light year over 12 months of continuous travel. This unit helps make galactic distances comprehensible by connecting them to time rather than trying to express enormous kilometer values. Consider what this means for observation. When we look at the galactic center, 26,000 light-years away, we see photons that departed there 26,000 years ago. We observe the center not as it exists now, but as it existed in the deep past. Similarly, hypothetical observers in the galactic center, looking toward our sun, would see it as it existed 26,000 years ago, well before human civilization emerged. Crossing our galaxy's full diameter would occupy light for 100,000 years of continuous travel. This establishes a fundamental limit, since nothing can exceed light's velocity according to special relativity. 100,000 years represents the minimum possible transit time for any signal or object crossing the galaxy. Actual material objects, being unable to reach light speed, would require even longer. Our Sun needs approximately 225 million years to complete one circuit around the galactic center. This orbital period, sometimes called a cosmic year or galactic year, provides perspective on timescales relevant to galactic processes. Since Earth formed roughly 4.5 billion years ago, our planet has witnessed about 20 of these grand orbits. The dinosaurs' age ended less than one cosmic year in the past. Their extinction occurred about 66 million years ago, less than 1/3 of a galactic orbit previous. All hominid evolution occupies only the most recent few million years, a tiny fraction of one orbital circuit. Recorded human history spans perhaps 10,000 years, which amounts to roughly 1/22,000th of a galactic year. This perspective helps calibrate thinking about galactic timescales. Processes that seem slow by human standards might be quite rapid by cosmic measures. Conversely, what appears static across human history might be changing substantially across galactic orbits. The spiral arms themselves, for instance, rotate at different speeds than stars orbit, creating the density wave pattern that triggers star formation. Rotation occurs throughout the galaxy, but the system doesn't spin like a solid wheel. Stars nearer the center complete their circuits faster than those farther out. A star at half our distance from the center might orbit in roughly 100 million years. A star twice our distance might require 400 million years. This rotation pattern doesn't follow what planetary systems exhibit. In the solar system, orbital velocity decreases with distance according to Kepler's laws. Mercury orbits faster than Earth, which orbits faster than Saturn. This pattern arises because nearly all the system's mass concentrates in the central sun. Galaxies behave differently because mass distributes more evenly throughout the structure. Visible matter alone would predict decreasing orbital speeds with distance, similar to planetary systems. Instead, observations show roughly constant velocities across wide ranges of galactic radius. This flat rotation curve provided key evidence for dark matter's existence. Some additional invisible mass component must be present to explain the observed rotation. Dark matter generates the gravitational forces necessary to maintain these constant orbital velocities. Current estimates suggest dark matter outweighs visible matter by roughly 5 to 1 in our galaxy. This invisible component doesn't emit, absorb, or reflect electromagnetic radiation in any detectable way. It reveals itself solely through gravitational effects on visible matter. Vera Rubin's rotation curve measurements in the 1970s provided convincing evidence for dark matter. By measuring how far stars orbit at various distances from galactic centers, she demonstrated that visible matter alone couldn't account for observed motions. Something additional must be present. Dark matter provided the explanation, though its exact nature remains one of astronomy's major unsolved questions. The spiral arms visible in photographs aren't permanent structures composed of the same stars continuously. Rather, they represent regions where density temporarily increases as stars and gas move through. Material enters an arm, experiences stronger gravitational forces from the enhanced density, slows slightly, then exits the other side once through the denser region. This creates zones of concentration that trigger new star formation. Gas clouds entering the spiral arms compress, sometimes enough to initiate gravitational collapse and star birth. Young, hot, massive stars born in these regions shine brightly but briefly, making the arms stand out visually. The arms appear bright, not because they contain permanently different stars, but because star formation rates increase there. Our Sun passes through these spiral features periodically as it orbits. The orbit isn't perfectly circular, so our distance from spiral arms varies over time. We encounter denser regions roughly every few 100 million years. Each passage might influence solar system conditions through increased cosmic ray exposure or gravitational perturbations affecting comet trajectories, though effects remain subtle and difficult to measure definitively. Between stellar systems, space contains gas and dust at extraordinarily low concentrations. The interstellar medium, as astronomers term it, averages about 1 hydrogen atom per cubic centimeter in our neighborhood. For comparison, Earth's atmosphere at sea level contains roughly 10 to the 19th molecules per cubic centimeter. Interstellar space is empty by any terrestrial standard. Despite this extreme sparseness, the material matters for several reasons. First, it provides the raw material for star formation. Molecular clouds, the densest regions of the interstellar medium, contain perhaps millions of atoms per cubic centimeter and serve as stellar nurseries. Second, even low average densities accumulate over light years. A spacecraft traversing thousands of light years would encounter substantial total mass. Third, the interstellar medium's chemical composition reveals galactic history. Composition reflects the galaxy's chemical evolution over billions of years. Hydrogen and helium, created in the Big Bang, dominate the mixture. Heavier elements like carbon, nitrogen, oxygen, and iron comprise perhaps 2% of total mass. These heavy elements originated in stellar interiors through nuclear fusion and dispersed through space when massive stars exploded as supernovae. Enrichment continues gradually. Each stellar generation forms from material slightly enriched by previous generations, produces additional heavy elements through fusion, and returns processed material to the interstellar medium through stellar winds or explosive death. Our solar system formed from material enriched by billions of years of this cycling. The iron in Earth's core, the oxygen we breathe, the carbon in our bodies all came from stellar nucleosynthesis in stars that lived and died before our Sun formed. The galactic center hosts a supermassive black hole designated Sagittarius A star, often written Sagittarius A star. This object contains roughly 4 million solar masses compressed into a region smaller than Mercury's orbital radius around the Sun. For context, Mercury orbits about 58 million kilometers from the Sun. The black hole's event horizon, the surface beyond which nothing can escape, measures only about 24 million kilometers across. Enormous mass occupies an extraordinarily compact volume. Radio observations reveal intricate structures surrounding SGR-A star. Curved loops of heated gas extend outward from the immediate vicinity. Regions of active star formation appear nearby, as gravitational tidal forces in the central regions apparently compress gas clouds enough to trigger star birth despite harsh conditions. Magnetic field lines thread through the area, revealed through polarization of radio emissions. Conditions near the center differ profoundly from our relatively calm environment in the Orion Arm. Stars orbit the central black hole at velocities reaching thousands of kilometers per second. Some stars complete orbits in just a few years, experiencing tremendous gravitational forces during close approaches. One star, designated S2, has been tracked through multiple orbits, providing opportunities to test general relativity in strong gravitational fields. Extending tens of thousands of light years above and below the galactic disk sit two massive structures of hot gas called the Fermi bubbles. NASA's Fermi Gamma Ray Space Telescope discovered these in 2010. They extend roughly 25,000 light-years above and below the galactic plane, spanning about 50,000 light-years total from top to bottom. The bubbles likely formed from some energetic episode at the galactic center, perhaps involving rapid accretion of material onto SGR-A star. When material falls toward a black hole, it heats up tremendously through friction and compression, often generating powerful outflows and jets perpendicular to the accretion disk. These outflows might have inflated the Fermi bubbles. Timing estimates suggest the bubbles formed only a few million years ago, quite recent cosmically. This demonstrates that galaxies undergo dynamic changes rather than remaining static. Periods of quiescence alternate with periods of activity. Our galaxy appears relatively quiet currently, but past episodes left marks like the Fermi bubbles that persist for millions of years. Most visible stars occupy the disk, but the Milky Way extends well beyond this flattened structure. An approximately spherical distribution of ancient stars and globular clusters surrounds the disk, forming what astronomers call the stellar halo. This halo extends perhaps 300,000 light-years from the galactic center, reaching far beyond the visible disk's 100,000 light-year diameter. Halo stars follow highly elongated orbits oriented at various angles relative to the disk's plane. Unlike disk stars moving in roughly circular paths around the center, halo stars follow eccentric ellipses that carry them far above and below the midplane, then back through it. These orbits reflect the halo's formation history, assembled from smaller systems that merged into the growing Milky Way early in its history. Globular clusters populate the halo. These dense stellar collections contain hundreds of thousands to millions of stars bound together in roughly spherical distributions. Individual globular clusters might span 50 to 100 light-years across. The stars within them orbit very close together by galactic standards, though actual collisions remain rare due to the vast spaces between individual stars even in these dense environments. Studying globular clusters illuminates the early galaxy's history. These clusters formed perhaps 12 to 13 billion years ago, within a few billion years of the Big Bang. Their stars contain very low heavy element abundances, reflecting formation from material not significantly enriched by stellar evolution. This low metallicity confirms great age, since each successive stellar generation forms from slightly more enriched material. Dating globular cluster stars helps constrain the galaxy's age. Various techniques suggest ages of 12 to 13 billion years for the oldest clusters, providing a lower limit on when the Milky Way began assembling. The galaxy itself might be slightly older than the oldest clusters, or they might have formed very early in the assembly process. Either way, these ancient systems preserve information about conditions in the early universe. Beyond the visible stellar halo, dark matter likely forms an even more extended halo, reaching several 100,000 light-years or more from the center. Precise boundaries remain uncertain, because dark matter reveals itself only through gravitational effects rather than emitting detectable radiation. Computer simulations of galaxy formation suggest these dark matter halos extend until they begin merging with neighboring galaxies' halos. Mapping the dark matter, halo's extent and structure presents significant challenges. Astronomers use several techniques. Rotation curves showing orbital velocities at various radii provide one method. Gravitational lensing, where the halo's mass bends light from background objects, offers another approach. Streams of stars torn from small satellite galaxies trace out the gravitational potential they orbit through, revealing dark matter distribution. These various methods paint a consistent picture. The dark matter halo extends far beyond visible structure. It likely follows a roughly spherical distribution, though probably not perfectly spherical. The halo's density decreases with distance from the center, but never drops to zero abruptly. Instead, it fades gradually, eventually becoming indistinguishable from the general cosmic background of dark matter permeating space. This describes our cosmic home's fundamental layout. We inhabit not a simple collection of stars, but rather a complex, multi-component gravitational system. Disk, bulge, stellar halo, and dark matter halo each represent distinct structures with different origins, different dynamics, and different stellar populations. Together, they create the system we call the Milky Way. Understanding this architecture becomes essential when considering departure from the system. The structure determines how gravity operates throughout the galaxy. It establishes the gravitational potential wells that bind objects to the system. It sets the escape velocities needed to break free. Any analysis of galactic escape must begin with this architectural understanding. Astronomical distances challenge human intuition because they exceed everyday experience by many orders of magnitude. We navigate daily life in meters and kilometers. Driving across a large country might cover 5,000 kilometers. Flying between continents spans perhaps 15,000 kilometers. These distances feel comprehensible because we can travel them within hours or days using available technology. Proxima Centauri, the Sun's nearest stellar neighbor, orbits roughly 4.2 light-years away. Translating this into familiar units reveals the scale. 4.2 light-years equals approximately 40 trillion kilometers. Earth's circumference measures about 40,000 kilometers. You could circle Earth 1 billion times and cover the distance to Proxima Centauri. While this distance counts as extremely nearby by galactic standards, it represents a vast separation when considering actual transit at achievable velocities. No current or foreseeable propulsion system can maintain speeds approaching those necessary to make interstellar travel practical on human timescales. The gulf between stars is simply immense relative to our transportation capabilities. Voyager 1, humanity's most distant spacecraft as of this writing, moves at approximately 17 kilometers per second away from the Sun. Launched in 1977, this probe has now left the heliosphere. the region dominated by solar wind, and the Sun's magnetic field. It travels through true interstellar space, though still gravitationally bound to the solar system and still far from reaching any other star. Maintaining Voyager's velocity, a journey to Proxima Centauri would span about 75,000 years. For context, anatomically modern humans emerged perhaps 300,000 years ago. Recorded human civilization spans perhaps 10,000 years. 75,000 years exceeds the entire span of human history multiple times over. This duration doesn't reflect engineering limitations or resource constraints in the usual sense. Voyager functions as designed, traveling through interstellar space following the laws of physics. The spacecraft will continue essentially forever, unless it collides with something or falls into a gravitational well. The limitation arises from the fundamental relationship between distance and velocity. The space between stars is vast. Achievable velocities are small compared to that vastness. Therefore, transit times become enormous. Voyager's plutonium power source continues generating electricity through radioactive decay heat. Power output decreases gradually as plutonium atoms transmute. Eventually, perhaps within the next decade, available power will drop below levels needed to operate instruments and transmit data back to Earth. The spacecraft will go silent but continue traveling indefinitely. Our galaxy's visible stellar disk extends roughly 50,000 light-years from our orbital position to its outer boundary. The dark matter halo reaches considerably farther, perhaps several 100,000 light-years. These numbers become more tangible when converted to travel times at known velocities. Using Voyager's speed as reference, traversing from our current location to the visible disk's edge would consume approximately 900 million years. This number strains comprehension. The universe itself is roughly 13.8 billion years old. 900 million years represents about 1/15 of cosmic history since the Big Bang. Complex multicellular organisms have existed on Earth for perhaps 600 million years. The entire age of complex life falls short of the time needed to cross our own galaxy at Voyager's velocity. Simple prokaryotic life existed much earlier, perhaps 3.5 billion years ago. Even that vast time span would only permit crossing the galaxy roughly 4 times. These comparisons reveal the scale mismatch between galactic distances and achievable spacecraft velocities. The numbers seem absurd because they are absurd by any human standard. Yet they arise naturally from combining measured astronomical distances with measured spacecraft speeds. The galaxy is genuinely that large relative to how fast we can travel. Travel time calculations assume straight-line paths at constant velocity through vacuum. Reality adds complications. Our solar system moves through the galaxy in complex ways. We orbit the galactic center at approximately 230 kilometers per second. We also oscillate up and down relative to the galactic midplane, crossing through it roughly every 30 million years. We move with respect to nearby stars in various directions depending on their individual orbits. Any departing vessel must account for these motions when plotting trajectories. The galaxy's rotation might aid or impede progress depending on chosen direction. Traveling in the direction of galactic rotation means moving with the general flow. Initial velocity relative to the galactic center starts at our orbital speed. Additional velocity must be added to that baseline. Traveling against rotation means first cancelling our orbital motion, then building up speed in the opposite direction. This requires more energy than traveling with rotation. Similarly, traveling perpendicular to the galactic plane versus within it presents different energy requirements due to our existing motion patterns. Though interstellar space appears empty by any terrestrial standard, it contains trace amounts of matter. An average of 1 atom per cubic centimeter might not sound significant. Earth's sea-level atmosphere contains roughly 10 to the 19th molecules per cubic centimeter. Interstellar space is genuinely a near-perfect vacuum by comparison. Still, particles at relativistic velocities represent a form of friction. A spacecraft moving at appreciable light speed fractions would experience continuous atomic impacts. Each collision releases energy. At high relative velocities, even hydrogen atoms striking a surface deliver substantial kinetic energy. The cumulative effect over thousands of light years would gradually erode shielding or generate radiation through collision heating. Robert Bussard proposed the interstellar ramjet concept in 1960. This theoretical spacecraft would deploy a large electromagnetic field, perhaps hundreds of kilometers across, to collect hydrogen atoms from space ahead of the ship. Collected material would fuel a fusion reactor, providing continuous propulsion. Elegant in principle, the concept faces formidable practical obstacles. The collection field must be enormous to gather sufficient material from such low densities. Even at relativistic speeds, hydrogen collection rates might not support continuous fusion. The fusion reactor must operate with extraordinary efficiency and reliability over timescales, far exceeding anything demonstrated. Most problematically, drag from collecting material might exceed thrust from burning it, preventing net acceleration at the speeds where the concept would provide most benefit. Reaching speeds approaching light velocity requires tremendous energy. Kinetic energy scales with velocity squared for non-relativistic speeds. Doubling velocity demands 4 times the energy. Triple velocity needs 9 times the energy. This relationship holds true in everyday experience and extends to higher speeds. Near light speed, special relativity effects emerge. An object's effective mass increases from external observers' perspectives as velocity rises. This doesn't mean the object gains physical mass, but rather that accelerating it requires progressively greater force. The relationship derived from Einstein's special relativity ensures no massive object reaches light speed itself. Doing so would demand infinite energy. The mathematics uses the Lorentz factor, represented by the Greek letter gamma. Gamma equals 1 divided by the square root of 1 minus v squared divided by c squared. Here v represents velocity and c the speed of light. At everyday speeds, gamma remains essentially 1. At 10% light speed, gamma equals about 1.005, a small but measurable correction. At 50% light speed, gamma reaches approximately 1.15. Time dilation and length contraction effects become noticeable at this point. At 90% light speed, gamma exceeds 2. Accelerating an object already moving at 90% light speed to 95% requires enormous additional energy despite the small velocity change. At 99% light speed, gamma approaches 7. These increasing gamma values translate to escalating energy requirements. Each additional increment of velocity costs more than the previous increment. The curve steepens dramatically approaching light speed. Practical limits arise long before reaching theoretical maximums. Achieving even 10% light speed with current technology appears extraordinarily difficult. Suppose advanced propulsion systems somehow reach 10% light speed. This represents roughly 30,000 kilometers per second, about 2,000 times faster than Voyager. Crossing the galactic disk's 100,000 light-year diameter would still require 1 million years at this velocity. 1 million years exceeds anatomically modern humans' entire existence by more than threefold. Homo sapiens emerged roughly 300,000 years ago. Every aspect of human evolution, culture, and technology development occurred within that span. A million-year journey dwarfs the entire human story thus far. Multiple generations would live and perish aboard any vessel attempting such a voyage. Even assuming extraordinarily long individual lifespans, perhaps 200 years through radical life extension, the journey would span 5,000 consecutive generations. For context, recorded human history reaches back perhaps 250 generations. Generation ships must support human populations across these timescales. Challenges extend far beyond propulsion and navigation. Such vessels require completely closed ecological systems with perfect material recycling. Every oxygen atom breathed, every water molecule drunk, every nutrient consumed must cycle through shipboard systems perpetually. Nothing can be wasted. Resources cannot be replenished from outside. Perfect recycling across thousands or millions of years seems extraordinarily difficult. Current Earth biosphere recycling occurs through complex interactions between countless organisms and geological processes. Recreating self-sustaining ecosystems in confined spaces remains an unsolved problem, even for short timescales measured in decades. Extending this to millions of years compounds difficulties enormously. Social stability must persist across not merely generations, but thousands or hundreds of thousands of generations. Maintaining consistent goals, values, and knowledge across such spans challenges imagination. Languages evolve, cultural norms shift, technologies advance or become obsolete, social structures transform. How would distant descendants relate to mission goals established by ancestors so remote as to be mythological? Consider language evolution. Modern English speakers struggle reading Middle English from 700 years ago without training. Old English from 1,000 years previous appears almost like a foreign language, despite continuous evolution. Over 100,000 generations aboard a generation ship. Language would transform beyond recognition countless times. Would the mission's final generation comprehend original documents? Would they care about objectives set by unimaginably ancient predecessors? Knowledge preservation presents similar challenges. Maintaining technical expertise required for ship operation and repair demands continuous training across countless generations. Any break in knowledge transfer could prove catastrophic. Key systems might fail without people who understand them. Complex technologies might be lost if not actively practiced and taught each generation. Motivation maintenance raises psychological questions. Early generations embark voluntarily with clear objectives. Middle generations are born into a journey they didn't choose, live their lives in transit, and die knowing descendants face identical circumstances. How do you maintain morale and purpose under such conditions? What psychological frameworks support people across such extended isolation? Genetic diversity requires careful management. Small populations risk inbreeding depression. Maintaining healthy genetic variation might demand populations of thousands or tens of thousands. This increases ship mass requirements, energy needs for life support, and social complexity. Larger populations ease some problems while creating others. Suspended animation offers an alternative to generation ships. Drastically slowing metabolism might allow individual travelers to survive journeys without significant aging. Unfortunately, no such technology currently exists. Biological obstacles appear formidable. Human bodies represent complex integrated systems that deteriorate even under ideal conditions. Cells accumulate damage from various sources. DNA experiences mutations. Proteins denature through thermal fluctuations. metabolic waste products accumulate. Preserving cellular integrity over millions of years while preventing aging requires understanding and controlling biological processes we barely comprehend currently. The challenge seems comparable to preserving a complex machine in perfect working order for millions of years without any maintenance. Some Earth organisms achieve limited suspended animation. Tardigrades enter cryptobiosis when facing extreme conditions, surviving vacuum, radiation, and temperature extremes for years. Some plant seeds remain viable across centuries. Certain bacterial spores allegedly survived millions of years, though these claims remain controversial. None involve preserving complex nervous systems or maintaining consciousness across dormant periods. Cryogenic preservation through freezing faces fundamental obstacles. Water expands when freezing. Ice crystals form during the freezing process, physically disrupting cellular structures. Cell membranes rupture, organelles damage. Even with cryoprotectant chemicals that reduce ice formation, damage appears severe at the cellular level. Some organisms tolerate freezing through natural cryoprotectants in their tissues. Wood frogs survive winter by allowing much of their body water to freeze while protecting critical organs. However, their nervous systems are relatively simple compared to mammals. No mammal has been cryopreserved and successfully revived. The damage from freezing appears too extensive for complex brains. These distance-related challenges exist before considering gravitational structure. We wouldn't cross empty void, but rather exit a gravitational system, extending hundreds of thousands of light years in all directions. The galaxy's total mass, distributed among stars, gas, and dark matter, generates a gravitational well. Objects within this well remain gravitationally bound, unless achieving escape velocity. Gravitational binding energy represents the total energy required to completely disperse a bound system. For the Milky Way, this energy is enormous, reflecting hundreds of billions of solar masses. Removing even a single solar system from this bound configuration demands overcoming its share of binding energy. While representing only a tiny fraction of the total, this fraction still amounts to vast energy by any practical standard. Earth escape velocity provides familiar context. Objects must reach roughly 11 kilometers per second to escape Earth's gravity without further propulsion. This represents the velocity where kinetic energy equals gravitational potential energy. An object achieving escape velocity can coast away indefinitely, gradually slowing due to gravity but never stopping or falling back. Solar system escape velocity from Earth's orbital distance reaches approximately 42 kilometers per second. This accounts for both Earth's gravity and the Sun's. A spacecraft must achieve this velocity relative to the Sun to leave the solar system permanently. Voyager spacecraft achieved this through planetary gravity assists, using Jupiter and Saturn encounters to gain sufficient velocity for solar system escape. Galactic escape velocity at our location reaches approximately 550 kilometers per second. This velocity would allow an object to coast away from the galaxy indefinitely against gravitational pull. The number depends somewhat on exact trajectory and assumptions about dark matter distribution, but 550 kilometers per second serves as a reasonable estimate. Our Sun currently orbits at roughly 230 kilometers per second. Achieving escape velocity requires adding approximately 320 kilometers per second to this existing motion in the appropriate direction. Since kinetic energy scales with velocity squared, this doesn't simply require doubling energy. The energy needed to accelerate from 230 to 550 kilometers per second substantially exceeds energy needed to accelerate from rest to 230 kilometers per second. These energy requirements vastly exceed current capabilities. Consider accelerating a modest spacecraft of 10,000 kilograms. Reaching escape velocity demands kinetic energy of roughly 1.5 times 10 to the 18th joules. This exceeds total annual human energy consumption. And this calculation only covers payload mass, before considering fuel, shielding, life support, or deceleration capability if planning to stop somewhere. Chemical rockets seem utterly inadequate for such velocities. Even optimistic fusion propulsion faces severe challenges. The energy must come from somewhere. It must be stored or generated somehow. It must accelerate the payload without destroying it through excessive acceleration forces. These constraints combine to make galactic escape extraordinarily difficult, even assuming peaceful development time measured in centuries. Time dilation provides slight consolation for hypothetical travelers at high velocities. Special relativity predicts that moving clocks run slower relative to stationary ones. For travelers at appreciable light speed fractions, subjective time would pass more slowly than coordinate time in the galaxy's reference frame. At 50% light speed, time dilation factor reaches about 1.15. A journey requiring 2 million years in the galaxy's frame would seem roughly 1.7 million years to travelers. Modest but noticeable reduction. At 90% light speed, the factor exceeds 2. A million-year journey seems roughly 500,000 years subjectively. At 99%, the factor approaches 7, reducing subjective journey time to roughly 140,000 years. However, time dilation doesn't reduce actual distance traveled or energy required. From any external perspective, the journey still requires full transit time. Travelers arrive far in the future relative to departure. If somehow returning, they'd find far more time elapsed at origin than they experienced during the round trip. This time, asymmetry, while fascinating, doesn't solve practical problems posed by distance. Light itself requires 100,000 years crossing the galaxy edge to edge. This establishes an absolute lower limit on transit time. No signal, no information, no material object can make the journey faster. Current physics prohibits faster than light travel except in highly speculative scenarios involving exotic matter with negative energy density or topological shortcuts through spacetime. Wormholes appear in general relativity solutions, but require exotic matter to remain stable and traversable. No evidence suggests this exotic matter exists. Creating a wormhole seems far beyond current or foreseeable capability. The concept remains theoretical speculation rather than engineering possibility. Warp drives, which could theoretically allow faster than light effective velocities by contracting space ahead and expanding space behind, face similar obstacles. The Alcubierre metric describing such drives requires exotic matter with negative energy density. Stability remains questionable. Energy requirements might approach cosmic scales. These concepts inhabit the realm of theoretical physics rather than practical engineering. Distance creates tyranny not through single factors, but through combined effects of vast spatial scales and the universe's fundamental speed limit. The galaxy is large. Light speed is finite. Material objects travel slower than light. These simple facts generate transit times exceeding human, civilizational, and evolutionary timescales. This analysis hasn't yet considered additional complications from gravity requiring sustained high velocity throughout transit, from universal expansion affecting what lies beyond gravitationally bound regions, from engineering practicalities of maintaining systems across such durations, or from biological and social challenges of extreme isolation. Distance alone, before addressing these additional factors, makes galactic escape extraordinarily difficult, if not effectively impossible for any realistic scenario. We've explored quite a bit of ground so far. The Milky Way spans 100,000 light-years, with our solar system positioned 26,000 light-years from the center. Distance alone creates formidable barriers to galactic travel, with even light requiring 100,000 years to cross from edge to edge. Material objects travel slower, extending journey times to millions or billions of years. These timescales exceed biological lifespans, civilizational continuity, and even evolutionary processes. Gravity shapes galactic structure through fields that extend far beyond what visible matter alone would create. The Milky Way's gravitational influence doesn't end at the visible disk, or even at the stellar halo. Instead, it reaches outward through increasingly tenuous regions, creating a gradual transition rather than a hard boundary. Understanding escape velocity provides a starting point for considering departure from the galaxy. Escape velocity represents the speed needed to break free from a gravitational field entirely, never to return. Near Earth's surface, escape velocity is about 11 kilometers per second. From the solar system, measured from Earth's orbital distance, it increases to around 42 kilometers per second. These numbers reflect the Sun's gravitational hold on objects at various distances. Galactic escape velocity depends on position. From our location in the Orion Arm, approximately 26,000 light-years from the galactic center, the escape velocity is roughly 550 kilometers per second. This is about twice our Sun's orbital speed around the galaxy. Our Sun currently moves at 230 kilometers per second in its orbit, meaning we would need to more than double that speed to permanently leave the gravitational pull of the Milky Way. This calculation assumes a direct radial escape, moving straight away from the galactic center. In practice, any spacecraft would need to account for its existing orbital motion, which might help or hinder depending on the chosen direction of departure. Moving in the direction of our orbital motion provides some initial velocity, but escaping the galaxy requires overcoming not just the pull from the visible stars, but also the gravitational influence of dark matter. Dark matter dominates the galaxy's mass budget. Current estimates suggest dark matter outweighs visible matter by roughly 5 to 1 in our galaxy. This invisible component reveals itself through its gravitational effects on stars and gas clouds, particularly in the outer regions of galaxies where rotation curves remain flat rather than decreasing, as would be expected from visible matter alone. The dark matter forms a halo extending far beyond the visible disk. This halo likely reaches several 100,000 light-years from the galactic center, perhaps merging with the dark matter halos of neighboring galaxies at its outermost extent. The exact distribution remains uncertain, but computer simulations of galaxy formation suggest a roughly spherical arrangement that becomes less dense with increasing distance from the center. This extended dark matter halo creates a gravitational field that weakens gradually rather than dropping off sharply. An object attempting to leave the galaxy would experience decreasing but never entirely absent gravitational pull for hundreds of thousands of light-years. The energy required to overcome this field accumulates throughout the journey, not just at the beginning. Consider the nested structure of gravitational fields. Earth orbits the Sun, held by solar gravity. The solar system orbits the galactic center, held by galactic gravity. The galaxy itself belongs to the local group of galaxies, bound together by their combined gravitational fields. Each level represents a deeper gravitational well, requiring additional energy to escape. The local group contains the Milky Way, Andromeda, Triangulum, and dozens of smaller dwarf galaxies. The combined mass of this collection creates its own gravitational binding. Even if we could escape the Milky Way itself, we would still orbit within the local group, unless we achieved the higher escape velocity needed to leave this larger structure entirely. Escape from the local group requires speeds approaching 1,000 kilometers per second or more, depending on position and direction. This represents roughly 4 times our current orbital speed around the galaxy. The energy requirements scale with the square of velocity, meaning doubling the speed requires 4 times the energy, and quadrupling it requires 16 times as much. Gravitational binding energy provides another way to conceptualize the challenge. The binding energy represents the total energy needed to completely disperse a gravitationally bound system. For the Milky Way, this energy is enormous, reflecting the combined mass of hundreds of billions of stars plus the surrounding dark matter. Removing even a single star system from this bound configuration requires overcoming a tiny fraction of this binding energy, but that fraction still represents vast amounts of energy by human standards. The galaxy's rotation complicates matters further. Objects don't just fall straight toward the galactic center, but rather orbit through the gravitational field. This orbital motion provides some resistance to inward pull, creating stable circular or elliptical paths. To escape, an object must gain enough velocity to transform this bound orbit into an unbound trajectory. The transition occurs at the escape velocity, where kinetic energy exactly equals gravitational binding energy. Zero-velocity surfaces offer a useful concept for visualizing gravitational boundaries. These surfaces mark regions where an object with zero velocity relative to the galaxy would begin falling inward. Inside these surfaces, objects are gravitationally bound. Outside them, objects can drift away without additional energy input. For the Milky Way, these surfaces likely extend to distances comparable to the dark matter halo, hundreds of thousands of light-years from the center. The gravitational field weakens with distance according to the inverse square law for point masses. But galaxies aren't point masses. Their extended structure creates more complex field patterns. Near the galactic center, the field strength increases dramatically. In the outer regions where we reside, it decreases more gradually due to the distributed mass of the disk and halo. This brings us to an important realization. Gravity doesn't create walls or barriers in the conventional sense. It creates gradients, slopes in the fabric of space-time that require energy to climb. The steeper the slope, the more energy needed. The Milky Way's gravitational field creates a very deep, very gradual slope extending enormous distances in all directions. Climbing out of this gravitational well while maintaining high speed throughout the journey represents the fundamental challenge of galactic escape. It's not impossible in principle, but it requires sustained energy expenditure over distances and timescales that dwarf anything in human experience. The bonds of gravity hold us not through absolute prohibition, but through energy requirements that currently exceed our technological capabilities by many orders of magnitude. The expansion of space adds another layer of complexity to galactic escape. While gravity binds nearby structures together, the universe as a whole expands, carrying distant galaxies away from each other at increasing speeds. This expansion doesn't affect objects within gravitationally bound systems like our galaxy or the local group, but it profoundly impacts what lies beyond these structures. Edwin Hubble's observations in the 1920s revealed that distant galaxies show redshifts in their spectra proportional to their distance. The farther away a galaxy sits, the faster it appears to recede. This relationship now called Hubble's law, reflects the expansion of space itself rather than motion through space. Galaxies aren't moving away from us through space. Rather, the space between us and them is expanding, carrying them along with it. The current expansion rate, known as the Hubble constant, is approximately 70 kilometers per second per megaparsec. A megaparsec equals about 3.26 million light years. This means that a galaxy located 1 megaparsec away recedes at 70 kilometers per second. A galaxy at 2 megaparsecs recedes at 140 kilometers per second, and so on. The relationship continues linearly for relatively nearby galaxies, but becomes more complex at cosmological distances. At some distance, the recession velocity equals the speed of light. Beyond this distance, galaxies recede faster than light can travel toward us through the expanding space. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Rather, space itself expands at this rate. The effective horizon this creates is called the Hubble sphere, and it sits roughly 14 billion light years away in all directions. For galaxies beyond the Hubble sphere, light emitted toward us makes no progress in our direction because space expands faster than the light moves through it. We can still see many such galaxies because we're observing light they emitted billions of years ago when they were closer and space expanded more slowly. However, we can never receive signals from events occurring in those galaxies today. Dark energy drives the accelerating expansion. This mysterious component of the universe, which constitutes about 68% of the total energy density, exerts a repulsive effect that causes expansion to accelerate over time. Observations of distant supernovae in the late 1990s revealed this acceleration, fundamentally changing our understanding of cosmic evolution. The acceleration means that galaxies currently beyond a certain distance will eventually move beyond any possible reach, even if we could travel at light speed. This reachability horizon sits much closer than the Hubble sphere, at roughly 16 to 18 billion light years, depending on various cosmological parameters. Galaxies beyond this distance are already unreachable by any future signal or spacecraft we might send, regardless of technological advancement. The local group remains gravitationally bound despite the expansion of space. The combined gravity of the Milky Way, Andromeda, and other member galaxies overcomes the expansion in this region. Think of expansion as a gentle outward force that affects all space uniformly. In regions where gravity is weak, such as the space between galaxy clusters, this outward force dominates and structures separate. In regions where gravity is strong, such as within galaxy clusters or groups, gravitational attraction overcomes expansion and structures remain bound. Our local group will remain bound indefinitely. Computer simulations of the far future suggest the Milky Way and Andromeda will eventually merge, probably in about 4 billion years, forming a single large elliptical galaxy. The smaller local group members will either merge with this combined structure or orbit around it. This process will create an island of gravitationally bound matter in an increasingly empty universe. The expansion affects what remains accessible over cosmic time. Currently, we can observe galaxies in the Virgo supercluster, the larger structure containing the local group, and many nearby galaxy clusters. The Virgo cluster itself sits about 50 to 60 million light years away. Galaxies in this cluster recede from us at speeds of several hundred to over 1,000 kilometers per second due to expansion. As time passes, expansion will carry more and more galaxies beyond the reachability horizon. The observable universe will continue expanding as light from more distant regions reaches us. but the reachable universe will shrink. Eventually, in hundreds of billions of years, observers in our galaxy will see only the local group in their telescopes. The rest of the universe will have receded beyond any possible observation or contact. This creates an interesting temporal asymmetry. We exist at a time when the observable universe contains hundreds of billions of galaxies spread across billions of light years. Future observers will see far fewer galaxies. Past observers would have seen galaxies closer together, with less expansion between them. Our cosmic perspective is time-dependent, shaped by when we happen to observe the universe. For practical purposes of galactic escape, expansion doesn't prevent leaving the Milky Way. The local group remains accessible despite expansion because gravitational binding dominates. However, expansion does limit the ultimate scope of possible exploration. Even if we could somehow traverse the local group, perhaps over millions of years, galaxies beyond it recede faster than we could ever travel toward them. The recession velocities compound over distance. A galaxy cluster 100 megaparsecs away recedes at 7,000 kilometers per second. At 200 megaparsecs, the recession velocity approaches 14,000 kilometers per second. These speeds far exceed anything achievable through chemical or nuclear rockets and approach velocities that would require relativistic physics to properly describe. Think about timing and coordination. If we aimed a spacecraft toward a distant galaxy receding at 1,000 kilometers per second, we would need to travel faster than 1,000 kilometers per second just to make up for the expansion occurring during the journey. The farther away the target, the faster it recedes, creating a moving finish line that accelerates away as we approach it. Within the local group, this problem doesn't apply because expansion is overcome by gravity. Andromeda actually approaches us at about 110 kilometers per second, despite expansion, because gravitational attraction between our galaxies dominates. The Magellanic Clouds orbit the Milky Way. Triangulum orbits within the local group. These motions reflect gravitational dynamics rather than cosmic expansion. The boundary of accessibility corresponds roughly to the boundary of gravitational binding. Structures bound together now will remain accessible, though reaching them might require millions of years of travel. Structures not currently bound will recede beyond reach. As expansion continues, this creates a natural division in the universe, a finite region of potentially accessible space surrounded by an ever-expanding realm that will remain forever beyond contact. Understanding expansion provides context for galactic escape questions. Leaving the Milky Way is extraordinarily difficult due to distance and gravity, but expansion doesn't make it impossible. Leaving the local group becomes practically impossible, not because of gravity alone, but because expansion carries more distant targets away faster than we could pursue them. The universe itself sets limits on travel range through its fundamental expansion dynamics. Let's pause to consider what we've covered. We began with galactic architecture, understanding the disk, bulge, and halos that compose our galaxy. We examined how distance creates practical barriers to travel, with journey times measured in millions of years, even at optimistic velocities. We've seen how gravity binds objects to the galaxy through escape velocities far exceeding our current orbital motion. Now we're exploring how space itself expands, adding another layer of complexity to long-distance travel. Consider what would be required for an actual journey beyond the galaxy. The distances involved transform theoretical possibilities into practical impossibilities through accumulated challenges of duration, resources, and reliability. A spacecraft traveling at 10% the speed of light, an optimistic target for advanced propulsion systems, would require 1 million years to cross the galaxy. This duration exceeds recorded human history by a factor of 200. It exceeds the existence of anatomically modern humans by a factor of 3. No human institution, no technological civilization, no biological species in Earth's history has maintained continuity over such timescales. Spacecraft longevity presents the first major challenge. Current deep space probes are designed for missions lasting decades. Voyager 1 and Voyager 2, launched in 1977, still function after nearly 50 years, but their power supplies will fail within the next decade. Their operational lifespan represents perhaps 70 years total, less than 1/10,000th the time needed for galactic crossing. Extending spacecraft lifetime to millions of years requires solving problems that don't exist on shorter timescales. Materials degrade through various processes. Cosmic rays damage electronic components. Micrometeorites erode surfaces. Thermal cycling stresses structural elements. These effects accumulate slowly but relentlessly over time. A spacecraft might survive decades or even centuries, but millions of years introduces degradation mechanisms that bypass any realistic redundancy or shielding. Radiation damage becomes severe over such durations. Cosmic rays, high-energy particles streaming through space from various sources, strike spacecraft continuously. Each impact can damage atoms in electronic components, creating defects that accumulate over time. Modern spacecraft include radiation-hardened components designed to withstand decades of exposure, but millions of years of continuous bombardment would eventually destroy any electronic system. The interstellar medium, though extremely sparse, becomes significant over galactic distances. At 1 hydrogen atom per cubic centimeter and speeds of 10% light speed, a spacecraft would encounter roughly 300 tons of matter per square meter of cross-section over 1 million years. This represents constant bombardment by atoms at 30,000 kilometers per second, each impact releasing energy comparable to a speeding bullet. Shielding against this requires mass, which must be accelerated and decelerated, increasing energy requirements substantially. Energy requirements scale dramatically with speed and duration. Accelerating 1 kilogram to 10% light speed requires about 4.5 times 10 to the 14th joules, equivalent to about 11 kilotons of TNT. A modest spacecraft massing 10,000 kilograms would need 4.5 times 10 to the 18th joules just for the payload, before considering fuel mass, shielding, or the fact that carrying fuel to decelerate at the destination roughly doubles the initial mass that must be accelerated. Nuclear fusion offers the most plausible propulsion method for achieving high speeds, but even optimistic fusion rockets face severe limitations. The specific impulse, a measure of propulsion efficiency, determines fuel requirements. Higher specific impulse means less fuel needed for a given velocity change. Fusion rockets might achieve specific impulses 10 to 100 times better than chemical rockets, but this still requires fuel masses comparable to or exceeding payload mass for journeys at significant fractions of light speed. Life support for biological passengers compounds these problems. Humans require continuous supplies of oxygen, water, and food, along with waste recycling and radiation shielding sufficient to prevent harmful exposure over decades. Extending this to millions of years transforms the spacecraft into a complete ecosystem that must maintain itself across timescales exceeding evolutionary adaptation. Generation ships, where multiple generations live and die during the journey, face biological and social challenges alongside engineering ones. Maintaining genetic diversity in a small population requires thousands of individuals. maintaining social stability and technical knowledge across hundreds of thousands of generations, each living in an artificial environment with no experience of planets or normal gravity, introduces uncertainties that may dwarf the engineering challenges. Navigation over galactic distances presents unique problems. The galaxy rotates, stars move in their orbits, and targeting a specific destination requires accounting for all these motions over the journey duration. A target star might move thousands of light years during a million-year journey, requiring continuous course corrections based on updated position measurements. The navigation computer must function reliably for the entire journey, updating trajectories based on observations made during flight. Communication with Earth becomes impossible over such distances and durations. Radio signals traveling at light speed would require tens or hundreds of thousands of years to cross the distance. By the time a signal sent from mid-journey reached Earth, whoever sent it would have died millennia ago, and whoever received it would have no living connection to the original senders. The mission would become utterly isolated, unable to receive assistance or updated instructions. Psychological factors intensify over extreme durations. For generation ship crews, every person would be born into a journey they didn't choose, live their entire life in transit, and die knowing that thousands of future generations must do the same before arrival. Maintaining motivation, cultural continuity, and operational competence across such timescales challenges assumptions about human psychology and social organization. Consider redundancy requirements. Any critical system must have backups, and those backups must have backups, accounting for failures over millions of years. The probability of failure-free operation decreases exponentially with time for any given component. Maintaining sufficient redundancy to achieve reasonable mission success, probability might require mass allocations that make the entire enterprise impractical. Manufacturing and repair capabilities during flight become essential for such durations. The spacecraft must be able to fabricate replacement parts for any system that might fail, using raw materials either carried from the start or collected during the journey. This requires carrying not just spare parts but spare manufacturing equipment, along with the knowledge and skills to use it across hundreds of thousands of generations. Even autonomous systems face severe challenges. A purely robotic mission eliminates biological life support requirements, but must maintain computing, sensing, and mechanical systems for millions of years without human intervention. Self-repair capabilities must extend to every component, including the systems that perform repairs. The complexity of such a system, required to operate longer than complex life has existed on Earth, seems beyond current engineering capabilities. The journey would occur in near total isolation from human civilization. Whatever launched the mission would have evolved, collapsed, or transformed beyond recognition, long before any signals from the destination could return to Earth. The mission exists in its own timeline, disconnected from the context that created it, pursuing goals that may have lost relevance to whoever set them originally. These practical considerations don't absolutely prohibit galactic travel, but they illustrate why theoretically possible and practically achievable diverge so completely on galactic scales. The accumulated challenges of time, distance, energy, and reliability create barriers that may prove as insurmountable as physical laws themselves. The galaxy becomes unreachable not because physics forbids the journey, but because the journey requires conditions that cannot be maintained across the required duration. Within the constraints we've explored, some regions of space remain potentially accessible. The local group contains enough structure to occupy exploration for timescales comparable to or exceeding any imaginable civilization duration. Understanding what lies within reach provides perspective on the boundaries we face. The local group spans roughly 10 million light-years across. It contains the Milky Way, Andromeda, Triangulum, and at least 80 dwarf galaxies. The combined mass approaches 2 trillion solar masses. This structure represents our cosmic neighborhood, bound together by gravity despite the universe's expansion. Andromeda, also called MM31, sits approximately 2.5 million light-years away. It's the largest galaxy in the local group, containing perhaps 1 trillion stars compared to our galaxy's few hundred billion. Andromeda approaches us at roughly 110 kilometers per second, and current models predict a collision or close passage in approximately 4 billion years. This approach occurs despite cosmic expansion, because gravitational attraction between the galaxies overcomes expansion in this region. A journey to Andromeda at 10% light speed would require 25 million years. This reduces the travel time compared to crossing our own galaxy, though it remains far beyond current capabilities. The destination offers substantial differences from our galaxy. Andromeda has a more massive bulge, a more extensive halo of globular clusters, and possibly different star formation histories that have created distinct stellar populations. Triangulum, or M33, lies slightly farther, at about 3 million light-years distance. It's considerably smaller than either the Milky Way or Andromeda, containing perhaps 40 billion stars. Triangulum orbits within the local group's gravitational field, possibly bound to Andromeda, though the exact orbital relationship remains uncertain. Reaching it would require timescales similar to those for Andromeda. The Large and Small Magellanic Clouds orbit our own galaxy at distances of roughly 160,000 and 200,000 light-years respectively. These dwarf irregular galaxies contain billions of stars and active star-forming regions. They're already within the Milky Way's gravitational influence, effectively part of our galactic system. Traveling to them would require only hundreds of thousands of years at 10% light speed, making them more accessible than intergalactic destinations while still presenting enormous challenges. Several dozen additional dwarf galaxies populate the local group. Most orbit either the Milky Way or Andromeda as satellites. These small galaxies contain millions to billions of stars and represent laboratories for understanding galaxy formation and evolution in low-mass systems. Many were discovered only recently through systematic sky surveys, and more likely await discovery. The local group will remain gravitationally bound indefinitely despite cosmic expansion. As the universe ages and expansion continues, this collection of galaxies will become increasingly isolated. In hundreds of billions of years, the local group will be the only structure visible to observers within it, surrounded by empty space as more distant galaxies recede beyond observability. Within the local group, specific targets offer scientific interest. Globular clusters around both our galaxy and Andromeda contain some of the oldest stars in the universe, formed within the first billion years after the Big Bang. Studying these systems up close could reveal details about early cosmic conditions and the first generations of star formation. Star-forming regions in nearby galaxies provide comparison points for understanding stellar birth. The spiral arms of Andromeda and Triangulum contain active regions where gas clouds collapse into new stars. Observing these processes in different galactic environments could illuminate how galaxy-scale properties affect star formation. Central regions of nearby galaxies host their own supermassive black holes. Andromeda's central black hole contains approximately 100 million solar masses, roughly 25 times more massive than our galaxy's Sagittarius A star. Studying how different mass black holes affect their host galaxies could reveal scaling relationships important for understanding galaxy evolution. The intergalactic medium within the local group contains gas at very low density, often heated to high temperatures by past interactions between galaxies. This material traces the gravitational potential of the group and might reveal characteristics of dark matter distribution that are difficult to observe through other means. Realistic exploration timescales extend to millions of years even for nearby targets. A mission to the Magellanic Clouds at 10% light speed would require roughly 2 million years for the complete journey, including deceleration at the destination. Doubling that for a return journey brings total mission time to 4 million years. Human anatomical characteristics have remained relatively stable for perhaps 300,000 years, suggesting that 4 million year missions exceed biological and possibly cultural continuity. One-way missions make more sense in this context. Send exploration probes or autonomous systems on journeys with no expectation of return. Let them study destination systems and relay findings back to us via radio signals that will take the same millions of years to arrive. Accept that whoever receives the data will have no living connection to whoever sent the probe, and will inhabit a civilization that has evolved in unpredictable ways during the interim. Several proposed mission concepts aim at interstellar travel within our galaxy. Breakthrough Starshot envisions light sails accelerated by ground-based lasers to 20% light speed, reaching the nearest stars within decades. Project Daedalus, designed by the British Interplanetary Society, proposed a fusion-powered spacecraft for reaching Barnard's star in 50 years. These concepts address travel within our galaxy rather than beyond it, but they illustrate the engineering challenges even for the nearest neighboring stars. Scaling these concepts to intergalactic distances multiplies challenges enormously. The energy requirements increase with distance and speed. The communication delays extend from years to millions of years. The probability of mission success decreases as journey duration increases. Yet none of this makes such missions impossible in absolute terms, only extremely difficult with current or foreseeable technology. The local group represents our cosmic future. As expansion carries more distant structures beyond reach, this collection of gravitationally bound galaxies will become the entirety of the accessible universe. Within it, billions of stars orbit, planets form, and possibly other civilizations exist. The scope of potential exploration, even limited to this region, vastly exceeds anything human civilization might accomplish over any plausible future timescale. Understanding this accessible region clarifies our cosmic context. We're not limited to a single star system or even a single galaxy, but we are limited to a specific collection of gravitationally bound structures. This defines the cosmic neighborhood available for exploration and development, a region large enough to contain more stars than humanity could ever individually study, yet small compared to the observable universe as a whole. Before moving forward, we can review the constraints we've identified. Galactic structure extends hundreds of thousands of light years through visible and dark matter components. Distance requires millions of years of travel time at achievable speeds. Gravitational binding demands escape velocities we cannot currently reach. Space expansion affects what lies beyond our local group. Yet within these boundaries, the local group offers billions of stars potentially accessible over extended timescales. Boundaries shape experience by defining what lies within and beyond reach. The impossibility of galactic escape creates such a boundary. raising questions about how we understand and respond to fundamental limits. Physical limits differ from social or political ones. Social boundaries can be negotiated, changed through agreement or force. Physical boundaries arise from natural laws that operate independently of human preferences. The speed of light, the strength of gravity, the expansion of space. These create constraints that no negotiation can modify. Accepting physical limits doesn't require abandoning ambition, but rather directing it toward what's actually possible. Within our accessible cosmic neighborhood, the local group, possibilities vastly exceed current capabilities or needs. Billions of stars orbit within this region. Countless planets circle those stars. The resources available dwarf anything humanity currently uses or could use in any foreseeable future. Consider the concept of horizon. A horizon represents the limit of what can be observed or reached from a given position. Earth's surface creates a visual horizon a few kilometers away for a person of average height. Mountains or tall buildings extend this horizon, but never eliminate it entirely. Similarly, cosmic horizons limit what we can see or reach, regardless of technological capability. These horizons aren't walls in any conventional sense. You don't encounter a barrier marking the boundary. Rather, conditions gradually become more extreme until continuation becomes impossible. Approaching a visual horizon, the ground simply curves away. Approaching a cosmic horizon, targets recede faster than you can pursue them, or gravity pulls stronger than you can escape. Philosophical traditions have long engaged with the question of limits and how humans respond to them. Stoic philosophy emphasized accepting what cannot be changed while working diligently on what can be. Existentialist thought explored how limitations define the context within which meaning emerges. Eastern contemplative traditions often focused on finding peace within natural constraints, rather than struggling against them. The recognition that we cannot escape the galaxy might prompt various responses. Some might view it as a tragedy, a fundamental limitation on human potential. Others might see it as irrelevant, given that accessible regions vastly exceed any realistic exploration capacity. Still others might find it oddly comforting, a clear boundary that eliminates certain anxieties about infinite possibility. Consider the alternative, a universe without boundaries. If every destination were reachable, if no horizon limited expansion, what would that mean? Goals would lose definition. Achievement would become arbitrary. The finite becomes meaningful partly because infinity remains beyond reach. We value completing a journey because we recognize that some journeys cannot be completed. Boundaries create definition. A bounded space has character, identity, specific properties that distinguish it from other spaces. The local group, our cosmic boundary, has specific characteristics, certain galaxies, certain structures, a specific arrangement of matter shaped by gravitational interactions over billions of years. This isn't just space in an abstract sense, but a particular region with particular properties. Human identity forms partly through engagement with boundaries. Individuals define themselves through choices made within constraints. Civilizations develop character through how they respond to limits. The recognition that the local group bounds our accessible universe might someday become part of human cultural identity, shaping how future generations understand themselves and their place in the cosmos. Think about nested boundaries. We evolved on Earth, one planet among many. Earth orbits the Sun, one star among hundreds of billions. The Sun orbits within the Milky Way, one galaxy among billions. The Milky Way exists within the local group, one cluster among countless others. Each level represents a broader context, but ultimately, the boundaries of the local group represent our final horizon. These boundaries don't diminish what's achievable within them. Earth's biosphere, bounded by atmosphere and gravity, contains extraordinary diversity and complexity. The accessible universe, bounded by gravity and expansion, contains more structure than humanity could explore in any conceivable timeline. The boundary defines context without limiting achievement in any practical sense. The impossibility of galactic escape might eventually unite humanity in a shared understanding. Currently, we divide ourselves along national, cultural, and ideological lines. The recognition that we all share a bounded cosmic home, that we're all residents of the same local group regardless of terrestrial differences, might provide perspective that transcends smaller divisions. Yet, boundaries can also create claustrophobia or resistance. Some individuals and cultures respond to limits by pushing against them, seeking to expand boundaries even when expansion seems impossible. This drive has led to remarkable achievements throughout history, from crossing oceans to landing on the moon. The same drive might someday push technological capabilities toward the limits of what physics allows. Understanding the difference between impossible and merely extremely difficult matters here. Galactic escape isn't prohibited by physical law. It's just extraordinarily challenging given the distances, energies, and timescales involved. Perhaps future technologies we can't currently envision will make such journeys feasible. Or perhaps the fundamental constraints will prove insurmountable, regardless of advancement. The question of meaning within boundaries remains philosophical rather than scientific. Science can describe the boundaries, their location, their nature, what creates them. But science cannot determine how we should respond to them emotionally or socially. That response emerges from human consciousness engaging with physical reality, creating meaning through interpretation. We exist within boundaries at every scale. Our lifespans are bounded by biological aging. Our activities are bounded by physical capabilities. Our civilization is bounded by available resources and sustainable practices. The cosmic boundary represented by the local group simply extends this pattern to the largest scale relevant to human concerns. Perhaps the appropriate response combines acceptance of the boundary with full engagement within it. Recognize that the local group defines our cosmic home. Accept that more distant regions remain forever beyond reach, and then turn attention to the extraordinary possibilities that exist within accessible regions. This doesn't require resignation, but rather realistic focus. The galaxy continues its rotation regardless of human interpretations. Stars form, evolve, and die according to physical processes that operated long before humans existed and will continue long after. The boundaries these processes create exist independent of how we feel about them. Yet our feelings and interpretations matter to us, shaping how we experience our cosmic context and choose to proceed within it. Looking ahead requires considering what humanity might accomplish within the boundaries we've identified. The local group, while cosmically local, offers scope for development that vastly exceeds current imagination or capability. Space habitats represent one approach to utilizing resources beyond Earth. Rather than seeking distant planets around other stars, we might construct artificial environments in space itself, using materials from asteroids, moons, and other celestial bodies. This sidesteps the challenge of finding Earth-like planets while providing controlled environments optimized for human habitation. The O'Neill cylinder concept, proposed by physicist Gerard O'Neill in the 1970s, envisions large rotating structures that create artificial gravity through centrifugal force. a cylinder several kilometers in diameter and 20 kilometers long, rotating to produce Earth-normal gravity on its inner surface, could house populations in the millions while providing complete control over internal environment. Building such structures requires capabilities beyond current technology, but nothing that violates physical law. The materials exist within our solar system. The energy needed for construction could be provided by solar power or fusion reactors. The engineering challenges are substantial but appear solvable with sufficient development time and resources. Dyson spheres or swarms, collections of solar panels orbiting a star to capture its total energy output, could provide power for advanced civilizations. Rather than collecting only the tiny fraction of a star's energy that falls on a single planet, such structures could harness the complete luminosity, providing energy supplies trillions of times greater than Earth currently uses. These concepts require thinking on timescales of centuries or millennia, rather than years or decades. Building the first space habitats might take generations. Developing asteroid mining sufficient to supply construction materials might take even longer. But nothing in these timescales approaches the millions of years required for intergalactic travel, making them far more plausible near-term goals. Within our own galaxy, thousands of stars sit within 100 light-years of Earth. At 10% light speed, these stars could be reached in 1,000 years or less. This remains far beyond current capability, but falls within imaginable future advancement. Establishing outposts around nearby stars could begin within thousands rather than millions of years. Von Neumann probes, self-replicating robotic spacecraft that could explore the galaxy autonomously, represent another possibility. Launch initial probes toward nearby stars. Upon arrival, they use local materials to construct copies of themselves, which then travel to additional stars. This exponential replication could explore the entire galaxy within a few million years, even at relatively modest travel speeds. The ethical questions surrounding self-replicating machines deserve consideration. Uncontrolled replication could consume resources in ways that harm existing ecosystems or prevent future biological evolution. Programming safeguards to prevent such outcomes, while maintaining functionality across millions of years, presents both technical and ethical challenges. Artificial intelligence might enable exploration timescales impossible for biological organisms. A sufficiently advanced AI could potentially survive millions of years of journey time, maintaining functionality through self-repair and adaptation. Such systems could explore distant regions and relay findings back to humanity without requiring biological life support or generation ship complications. Creating AI with these capabilities remains speculative, but development over the next few centuries might produce systems far more capable than current technology. Whether such systems should be considered explorers representing humanity or independent entities with their own status raises philosophical questions about identity, consciousness, and representation. Terraforming planets around nearby stars offers another long-term possibility. Mars demonstrates some potential for environmental modification within our own solar system, though the challenges are substantial. Planets around other stars might offer better starting conditions or might require even more extensive modification, depending on their initial states. The timescales for terraforming extend to centuries at minimum, possibly millennia for complete transformation. But again, these timescales fall far short of intergalactic travel requirements. Focusing on what can be accomplished over thousands or tens of thousands of years, rather than millions, provides more realistic goal setting. Genetic modification of humans or development of post-human species adapted to space environments represents another possibility. Rather than creating Earth-like environments in space, we might adapt ourselves or our descendants to survive in conditions radically different from Earth. This raises profound questions about identity and continuity, but falls within the scope of imaginable future biotechnology. The resources available within our solar system alone exceed current use by vast margins. Asteroid belt mass totals roughly 3% of Earth's mass. Enough material exists to construct millions of large space habitats without depleting available resources significantly. The energy arriving from the Sun every second vastly exceeds total human energy consumption. Expanding to nearby star systems multiplies available resources enormously. Each stellar system contains planets, asteroids, comets, and other bodies that could provide raw materials. Each star provides energy. Thousands of such systems sit within reachable distance over timescales of centuries to millennia. The accessible universe, limited to the local group, contains resources that dwarf even this abundance. Billions of stars, each potentially surrounded by planetary systems, each providing energy and materials. The limitation isn't resources, but rather the timescales required to reach and utilize them. Population growth within space habitats could eventually produce numbers far exceeding Earth's capacity. If space habitat development continues over millions of years, populations could reach trillions or quadrillions, distributed across countless artificial environments throughout the accessible galaxy. Earth's current 8 billion represents a tiny fraction of potential future population. Such growth isn't necessarily desirable and might not occur for numerous social, economic, or philosophical reasons. But the possibility exists within physical constraints, illustrating that boundaries on cosmic exploration don't imply boundaries on development within accessible regions. Cultural evolution over such timescales becomes unpredictable. Human culture has changed dramatically over the past 10,000 years. Projecting millions of years into the future encounters fundamental uncertainty about what humanity or its descendants might become. We can identify physical possibilities, but cannot predict whether they'll be pursued or what values might guide such choices. Long-term stability requires sustainable practices. Growing without limit eventually encounters resource constraints even in the vastly resource-rich environment of space. Developing sustainable approaches to energy use, material cycling, and ecosystem management becomes essential for very long-term continuation. The vision of gradual expansion throughout the local group over millions of years provides an alternative to dreams of unlimited cosmic conquest. Rather than imagining journeys to the edge of the observable universe, we might envision careful, deliberate development of our actual cosmic neighborhood, creating sustainable civilizations around accessible stars. This vision doesn't require abandoning ambition, but rather directing it toward achievable goals. The local group offers scope for development that could occupy humanity for millions or billions of years. Within this bounded region, the opportunities for growth, exploration, discovery, and achievement vastly exceed anything feasible on Earth alone. The future within reach remains vast. Our boundaries don't limit us in any practical sense, but rather define the context within which development occurs. Working within these boundaries, humanity or its descendants might achieve remarkable things, while accepting that some regions of the universe will always remain beyond reach. Understanding galactic distances requires translation into terms more relatable than light years and parsecs. Analogies and scale models help build intuition about the true scope of cosmic structures. If we scale the solar system so that Earth's orbit around the Sun measured 1 meter across, The nearest star would sit roughly 270 kilometers away. On this scale, the Milky Way would span about 8 million kilometers, roughly 20 times the distance from Earth to the Moon. Andromeda would lie 200 million kilometers away, roughly the actual distance from Earth to the Sun. These scale distances illustrate why interstellar and intergalactic travel present such different challenges than interplanetary exploration. Moving between planets in our solar system, even at current spacecraft speeds, requires months to years. Moving between stars at those same speeds would require tens of thousands of years. Moving between galaxies would require billions of years. Consider time rather than distance. Light from the Sun reaches Earth in about 8 minutes. Light from the nearest star takes 4 years. Light from the galactic center takes 26,000 years. Light from Andromeda takes 2.5 million years. Each step up in distance creates proportional increases in travel time at any given speed. Energy comparisons provide another perspective. The total energy humanity currently uses in a year, all electricity generation, all fuel combustion, all energy consumption combined, totals roughly 500 exajoules. Accelerating a single kilogram to 10% light speed requires about 4.5 times 10 to the 14th joules, or about 1% of annual human energy use for each kilogram of payload. A modest spacecraft massing 10,000 kilograms would require energy equivalent to total human consumption for several years just for acceleration, before considering fuel mass, life support, or the energy needed to decelerate at the destination. Scaling this to the masses required for generation ships or substantial payloads pushes energy requirements to significant fractions of stellar output. Stars provide the only energy source sufficient for such requirements. Our Sun outputs roughly 3.8 times 10 to the 26th watts continuously. Harnessing even a tiny fraction of this output would provide energy vastly exceeding current human use. Dyson spheres or similar concepts represent attempts to capture more substantial fractions of stellar energy for civilization use. The mass of spacecraft required for long-duration missions creates additional scaling challenges. Current spacecraft mass a few hundred kilograms to a few tons. Space stations mass several hundred tons. Generation ships capable of supporting populations for millions of years would mass thousands or millions of tons, requiring construction capabilities far beyond anything currently achievable. Launch costs from Earth currently run thousands of dollars per kilogram. Even with substantial technological advancement reducing costs, launching millions of tons into space would require resources on the scale of significant fractions of global economic output, sustained over many years or decades. Population scales matter for generation ships. Maintaining genetic diversity requires populations of at least several thousand individuals. Providing living space, life support, agriculture, manufacturing, and all other necessities for such populations requires enormous habitat volumes. The spacecraft grows from a vessel into a mobile habitat, essentially a small city in space. Compare the volumes involved. The International Space Station provides roughly 1,000 cubic meters of pressurized volume for 6 to 7 crew members. Scaling to thousands of inhabitants requires millions of cubic meters, approaching the volume of large buildings or small mountains. Moving such structures at significant fractions of light speed requires energy approaching the total output of stars over substantial time periods. The number of stars within various distances from Earth provides perspective on exploration scope. Within 10 light years sit roughly 12 stars, mostly small red dwarfs. Within 100 light years, roughly 14,000 stars. Within 1,000 light years, roughly 100 million stars. The numbers grow rapidly as the search radius expands. Yet even 100 million stars represents less than 1% of the galaxy's total. Exploring them all, visiting each briefly, would require millions of years, even with very optimistic travel speeds. Thorough study of each system would extend timescales to billions of years, approaching the total age of the universe. Astronomical numbers lose meaning without careful consideration. Saying the galaxy contains hundreds of billions of stars provides a fact, but not necessarily understanding. Breaking it down helps. If you could visit one star per second, it would take roughly 10,000 years to visit all the stars in the galaxy. If each visit required 1 year, the total time extends to hundreds of billions of years, vastly exceeding the current age of the universe. These perspectives emphasize that galactic-scale exploration faces limits not from physics prohibiting it, but from physics making it impractical. The energy requirements, travel times, and resource allocations needed approach or exceed what physical systems can sustain, even under very optimistic assumptions about future capability. Focusing on what's achievable over realistic timescales provides better perspective. Exploring nearby stars over thousands of years, challenging but conceivable. Exploring the local galactic neighborhood over hundreds of thousands of years, very difficult but not obviously impossible. Exploring the entire galaxy, impractical regardless of technology. Exploring beyond the galaxy, effectively impossible, given current physics understanding. The distinction between different types of impossibility matters. Some things are impossible because they violate physical laws. Traveling faster than light, creating energy from nothing, reversing entropy in closed systems. Other things are impossible because they require conditions that cannot be maintained. Exploring the entire observable universe within a human lifetime, visiting every star in the galaxy, escaping to distant galaxy clusters. The latter category might become merely extremely difficult with sufficient technological advancement, but the gap between current capability and what would be required is so vast that treating them as impossible provides a reasonable approximation for practical planning purposes. Scale perspectives also illuminate why certain common science fiction scenarios seem implausible. Galactic empires controlling millions of stars face communication delays of thousands of years between distant outposts. News from one side of the empire would be ancient history by the time it reached the other side. Coordinated responses to events become impossible. The empire fragments into independent regions simply through communication lag. Similarly, stories of interstellar wars face the problem that sending military forces between stars requires decades or centuries at minimum. By the time forces arrive, the political situation that motivated the war might have completely changed. The energy expenditure to accelerate weapons or spacecraft to speed sufficient for interstellar travel would likely exceed the value of any conceivable objective. These scaling considerations don't make such scenarios absolutely impossible, but rather highlight why they're improbable under known physics. Science fiction often assumes technologies that bypass these constraints: faster than light travel, instantaneous communication, artificial gravity, unlimited energy. These technologies might exist in fictional universes, but don't exist in ours, making scenarios that depend on them unhelpful for understanding our actual cosmic context. The scale of the universe humbles human ambition in some ways, while validating it in others. We cannot explore everything, visit everywhere, understand every detail. But we can observe distant structures through telescopes, deduce their properties through analysis, and build theoretical frameworks that explain phenomena we'll never directly experience. understanding extends beyond direct exploration. Our cosmic perspective emerges from this interplay between limitation and capability. We're tiny beings on a small planet orbiting an ordinary star in a typical galaxy. Yet we've developed understanding that spans from quantum mechanics to cosmic evolution, from subatomic particles to the structure of the universe. This achievement matters even if physical exploration remains confined to a tiny fraction of what we can observe and understand. We've covered substantial ground in our exploration. The physical constraints, distance, velocity limits, gravitational binding, cosmic expansion, combine to make galactic escape extraordinarily difficult. These aren't arbitrary limitations, but consequences of the universe's fundamental structure. Understanding these boundaries helps clarify what remains achievable within our cosmic neighborhood and what lies permanently beyond practical reach. The space between galaxies differs fundamentally from the space between stars. Understanding this difference clarifies why intergalactic travel presents challenges beyond mere distance. Interstellar space, the region between stars within our galaxy, contains roughly 1 hydrogen atom per cubic centimeter on average. This represents extremely low density by terrestrial standards, far better than any laboratory vacuum. Yet over light years of distance, this sparse material accumulates into substantial mass that affects travel. Intergalactic space contains far less matter. The density drops to perhaps 1 hydrogen atom per cubic meter in the space between galaxies, 3 orders of magnitude less than interstellar space. Some regions contain essentially nothing, densities approaching what physicists call the quantum vacuum, where particle-antiparticle pairs briefly emerge from and return to empty space. This extreme emptiness creates unique conditions. Temperatures in intergalactic space approach absolute zero, cooled by the expansion of the universe to just a few degrees above the minimum possible temperature. Without nearby stars to provide heat or light, an object in intergalactic space would radiate away its thermal energy into the void, cooling toward the cosmic microwave background temperature of about 2.7 Kelvin. Navigation through intergalactic space lacks the reference points available within galaxies. Within the Milky Way, stars provide navigation references visible from most locations. In intergalactic space, the nearest navigation references might be millions of light-years away, appearing as faint smudges of light rather than individual stars. Precise position determination becomes extremely difficult without clear reference points. Cosmic rays, high-energy particles streaming through space, originate from various sources including supernovae and active galactic nuclei. Within galaxies, magnetic fields deflect and scatter these particles somewhat. In intergalactic space, the lack of significant magnetic fields allows cosmic rays to travel in straighter paths, but also means spacecraft would encounter less shielding from the galactic environment. Dark matter concentrations differ between galactic and intergalactic regions. Galaxies sit within dark matter halos that concentrate this invisible material. Intergalactic space contains dark matter at much lower average density, though the exact distribution remains uncertain. This affects gravitational fields experienced by objects traveling through these regions. The concept of zero-velocity surfaces helps visualize gravitational boundaries. These surfaces mark regions where an object with zero velocity relative to the local frame would begin falling toward a gravitating mass. For the Milky Way, these surfaces likely extend several 100,000 light-years from the galactic center, marking the approximate boundary of gravitational binding. Beyond these surfaces, in true intergalactic space, objects no longer fall toward our galaxy, but rather drift in the general expansion of the universe or fall toward other nearby gravitating systems. The transition isn't abrupt, but rather gradual, with gravitational influence decreasing continuously with distance. The local group's collective gravity creates its own zero-velocity surfaces encompassing all member galaxies. Objects inside these surfaces orbit within the local group. Objects outside them participate in cosmic expansion, receding from the group as space expands. The boundary sits roughly 5 million light-years from the group's center of mass. Traveling through intergalactic space requires maintaining spacecraft systems for durations exceeding those for interstellar travel by factors of hundreds or thousands. If interstellar travel to nearby stars requires centuries, intergalactic travel requires millions of years. The accumulated degradation over such timescales makes mission success probability approach zero for any conceivable technology. Energy requirements for intergalactic missions exceed those for interstellar missions proportionally with distance. A journey to Andromeda at 10% light speed requires 25 million years and energy sufficient to accelerate the payload to that speed. Carrying sufficient fuel, assuming fusion propulsion, might double or triple the initial mass, compounding energy requirements further. Communication across intergalactic distances creates unique challenges. A radio signal sent from a spacecraft halfway to Andromeda would require over 1 million years to reach Earth. By that time, human civilization as we know it would likely have evolved into something unrecognizable or cease to exist. The signal would be a message from a long-dead crew to recipients who share no cultural continuity with the senders. Consider the isolation this creates. A spacecraft in intergalactic space sits millions of light years from any substantial concentration of matter or energy. No help can arrive in less than millions of years should something go wrong. No communication provides information or guidance. The mission proceeds completely autonomously, isolated from the civilization that launched it. This isolation differs qualitatively from anything in human experience. Antarctic research stations experience isolation, but can be reached in days or weeks if necessary. Interplanetary spacecraft can receive instructions from Earth within hours. Interstellar missions might face decades of communication delay, but intergalactic missions face millions of years of absolute isolation from any external support or contact. Psychological effects of such isolation on crew members, even theoretical crew members, seem impossible to predict. Every psychological study of isolation involves durations of months or years at most. Extrapolating to millions of years, where thousands of generations live and die knowing no one will ever arrive at the destination during their lifetime, enters completely unknown territory. The emptiness itself might affect psychology. Within a galaxy, stars fill the sky, providing visual connection to cosmic context. In intergalactic space, looking away from the destination galaxy might show almost nothing, just the faint smudges of distant galaxies billions of light years away. The sense of isolation from seeing literally nothing in most directions could create psychological pressures unlike anything humans have experienced. The utility of intergalactic travel becomes questionable when examined closely. What could be learned by physically traveling to another galaxy that couldn't be learned through remote observation? Spectroscopy reveals chemical composition. Photometry measures brightness and distance. Radio and X-ray observations show energetic processes. Physical presence adds little to this knowledge, while requiring resources beyond any reasonable allocation. Scientific instruments can observe distant galaxies in extraordinary detail without leaving our own galaxy. The James Webb Space Telescope observes galaxies billions of light years away, studying their structure, composition, and evolution. Future telescopes might achieve even better resolution and sensitivity, providing detailed observations of individual stars in nearby galaxies like Andromeda. The resources required for a single intergalactic mission might instead support thousands of advanced observatories, providing far more scientific return. The energy needed to accelerate one spacecraft to a significant fraction of light speed could power entire civilizations for thousands of years. The cost-benefit analysis favors observation over exploration for intergalactic distances. This doesn't make intergalactic travel impossible in some absolute sense, only spectacularly impractical and unlikely to occur, unless driven by non-scientific motivations. Perhaps future civilizations might send missions for symbolic or philosophical reasons rather than practical ones. But such decisions would reflect values and priorities completely foreign to current human civilization. The isolation of galactic systems creates natural divisions in the universe. Each galaxy or galaxy group represents an island of matter and energy in an otherwise empty void. These islands remain gravitationally bound despite universal expansion, but they grow increasingly isolated from each other as expansion continues. The universe fragments into separate domains with diminishing connection to each other. Our domain, the local group, contains sufficient complexity to occupy any conceivable exploration effort. The isolation from other domains doesn't limit what we can achieve within our own, but rather clarifies that achievement will occur within a specific bounded context rather than extending without limit throughout the cosmos. The Milky Way represents more than an astronomical structure. It's the context within which Earth formed, life evolved, and human consciousness emerged. Understanding this relationship provides perspective on questions of cosmic belonging. Every atom heavier than hydrogen and helium in your body was forged in stars that lived and died before our sun formed. Carbon, nitrogen, oxygen, calcium, iron. All these elements came from stellar nucleosynthesis and were scattered into space by supernova explosions. The molecular cloud that collapsed to form our solar system contained these elements, incorporated from previous generations of stars. This process occurred within the galaxy. The stars that created these elements orbited through the Milky Way's disk, lived their lives, and ended in explosions that enriched the interstellar medium. That enriched material eventually collected into new molecular clouds, one of which became our solar system. We are, quite literally, made of galactic material processed through stellar evolution. The Sun's position in the galaxy affects Earth's habitability. We orbit in a relatively quiet region, away from the radiation-intense central area, but within the galactic disk where heavy elements exist in sufficient abundance for planet formation. This region, sometimes called the galactic habitable zone, provides conditions conducive to stable planetary systems and potentially complex life. Galactic rotation has carried our solar system through different regions of the Milky Way over its 4.5 billion year history. We've passed through spiral arms, where star formation and supernova rates increase. We've traversed quieter regions between arms. Each passage exposes Earth to different cosmic ray fluxes and different rates of nearby supernova events. Some researchers suggest these galactic influences might affect Earth's climate and biological evolution. Passing through spiral arms could increase cosmic ray flux, potentially, affecting cloud formation and climate. Nearby supernovae might influence atmospheric chemistry or even trigger mass extinctions. The evidence remains uncertain, but the possibility illustrates how galactic contexts might shape planetary evolution. The Sun's orbit around the galactic center creates a different kind of year, the galactic year of approximately 225 million Earth years. Our planet has completed roughly 20 such orbits since formation. The dinosaurs appeared and went extinct within a single galactic year. All of human evolution, from early hominids to modern civilization, represents just a tiny fraction of our current galactic orbit. This temporal context reminds us that while we exist within the galaxy temporarily, the galaxy exists across timescales that dwarf biological evolution. Stars have formed, evolved, and died multiple times over the galaxy's existence. The current structure represents a snapshot in ongoing evolution that began billions of years ago and will continue billions of years into the future. Chemical evolution of the galaxy creates a history written in stellar composition. Early stars formed from nearly pure hydrogen and helium, the primordial elements created in the Big Bang. These first-generation stars contained almost no heavy elements. When they exploded, they seeded space with the first heavy elements, enriching the material available for the next generation. Each successive generation of stars formed from slightly more enriched material. Our Sun, a third-generation star or later, formed from material already containing about 2% heavy elements by mass. This enrichment made possible the formation of rocky planets like Earth and the complex chemistry necessary for life. The galaxy continues this enrichment process. Current star-forming regions create new stars from material enriched by all previous stellar generations. Future generations of stars will form from even more enriched material, potentially making planetary systems quite different from our own in composition and characteristics. Understanding our galactic context suggests a kind of cosmic genealogy. We descend, in a sense, from specific stars that lived and died in specific parts of the galaxy's history. The elements in our bodies came from those stars. Our existence depends on galactic processes that operated over billions of years before Earth formed. This creates a relationship to the galaxy different from merely residing within it. We're not just located here. We emerge from galactic processes. The galaxy isn't simply our address, but rather our origin, the system that created the conditions necessary for our existence. Place-based thinking suggests that our relationship to location shapes identity and belonging. Humans have historically developed strong connections to specific places on Earth. Finding identity and meaning through relationship to particular landscapes, ecosystems, or regions. Perhaps a mature cosmic civilization might develop similar connection to its galactic context. Currently, most humans have little conscious awareness of existing within a galaxy. We know intellectually that the Milky Way exists and that we're part of it, but this knowledge rarely shapes daily experience or identity. A future civilization spanning many star systems might develop stronger galactic consciousness, understanding themselves as Milky Way beings whose identity connects fundamentally to this specific galactic structure. Such identity wouldn't require denying other aspects of individual or cultural identity, but rather adding galactic context to the layers through which we understand ourselves. Just as people can identify with a city, a region, a nation, and humanity as a whole simultaneously, they might identify with Earth, the solar system, the Orion Arm, and the Milky Way as nested contexts of belonging. The impossibility of galactic escape reinforces this potential identity. If the Milky Way truly represents our permanent home, then developing conscious relationship to it makes sense. We might cultivate appreciation for its structure, concern for its future, and sense of responsibility for how human activity affects it, similar to how environmental movements cultivate relationship to Earth's biosphere. This doesn't require mystical or supernatural beliefs, but rather recognition of relationship and interdependence. We exist because of galactic processes. We're made of galactic material. Our future, whatever it holds, will unfold within galactic context. These facts create a relationship, whether we consciously acknowledge it or not. Philosophy has long engaged with questions of home, belonging, and rootedness versus wandering. Existential philosophy explored how humans create meaning through engagement with their context. Environmental philosophy developed concepts of place-based identity and belonging to ecosystems. Cosmic philosophy might extend these concepts to galactic scales. The question of cosmic loneliness, whether other intelligences exist in the universe, takes on different weight when considering galactic boundaries. If we're alone in the Milky Way, then the galaxy represents our sole domain, perhaps to be cherished more carefully for its uniqueness. If other intelligences exist within our galaxy, then we share this cosmic home with others, creating potential for connection and relationship within our accessible region. Either way, the galactic context shapes what's possible and meaningful. Whether we explore outward to meet others or remain solitary in our development, the activities unfold within the Milky Way's structure and bounds. The galaxy provides the stage for whatever cosmic story humanity or its descendants might write. Understanding home at galactic scale doesn't diminish Earth's importance, but rather situates it within broader context. Earth remains our immediate home, the planet that gave rise to life and consciousness. But Earth exists within the solar system, which exists within the galaxy, which exists within the local group. Each level provides context for the next, creating nested structures of belonging. The recognition that we cannot escape the galaxy might ultimately prove liberating rather than limiting. It clarifies where our future actually lies, focuses attention on accessible possibilities rather than impossible dreams, and creates opportunity for developing conscious relationship to our actual cosmic context. The galaxy becomes home not through choice, but through physical reality, and perhaps wisdom lies in accepting and even embracing this fact. Taking stock of our journey so far, we've examined galactic architecture, the tyranny of distance, gravitational bonds, and space expansion. We've considered practical challenges of maintaining systems across required timescales and explored what regions remain accessible. We've reflected on the meaning of these boundaries and looked at futures possible within them. The picture that emerges shows clear limits, but also vast possibilities within those limits. Understanding the galaxy doesn't require traveling through it. Human knowledge of cosmic structures comes primarily from observation at various wavelengths. Creating detailed pictures of systems we'll likely never visit physically. Galileo first resolved the Milky Way into individual stars in 1610, using a primitive telescope. Before this, the band of light across the sky was known, but not understood. His observations revealed it as countless distant stars too faint and numerous to distinguish individually with the naked eye. William Herschel mapped the distribution of stars in the late 1700s, attempting to determine the galaxy's structure from our position within it. He assumed stars were distributed uniformly in all directions and used star counts to estimate distances. While his specific conclusions proved incorrect due to this flawed assumption, his approach established systematic observation as a path to understanding galactic structure. Harlow Shapley's work in the early 1900s revealed the Sun's position away from the galactic center by studying globular cluster distribution. These dense star clusters orbit through the galactic halo, and Shapley found they concentrated around a point in the direction of Sagittarius, roughly 26,000 light-years away. This demonstrated that our solar system occupies a position far from the galactic center, ending earlier assumptions that we resided near the middle. The development of radio astronomy in the mid-20th century allowed observation through the dust that obscures visible light views of much of the galaxy. Radio waves pass through dust clouds that block optical light, revealing the galaxy's structure, including the spiral arms, central regions, and distribution of gas throughout the disk. The 21-centimeter hydrogen line proved particularly important for mapping galactic structure. Neutral hydrogen atoms emit radio waves at this specific wavelength, and since hydrogen is the most abundant element in the galaxy, detecting this emission allows mapping of gas distribution throughout the Milky Way. Doppler shifts in the emission reveal rotation velocities, allowing calculation of the galaxy's rotation curve. Infrared observations, developed extensively in the late 20th and early 21st centuries, penetrate dust even better than radio waves while providing different information. The Spitzer Space Telescope and other infrared missions mapped stellar populations throughout the galaxy, revealing the central bar structure and refining understanding of spiral arm configuration. X-ray and gamma-ray observations reveal the most energetic processes in the galaxy. The Chandra X-ray Observatory and Fermi Gamma-ray Space Telescope observe phenomena like supernova remnants, neutron stars, black holes, and the exotic environment near the galactic center. These high-energy observations complement lower-energy studies, creating a multi-wavelength picture of galactic structure and activity. Computer simulations based on observational data allow reconstruction of the galaxy's three-dimensional structure from our limited perspective within it. By combining observations at multiple wavelengths with models of stellar evolution, gas dynamics, and gravitational interactions, astronomers create detailed maps of galactic components, even though we can only observe from a single vantage point. The discovery of dark matter through its gravitational effects exemplifies how observation reveals phenomena that cannot be directly seen. Vera Rubin's measurements of galaxy rotation curves in the 1970s showed that visible matter alone couldn't account for observed rotation speeds. This led to the hypothesis of dark matter halos, now supported by multiple independent lines of evidence from gravitational lensing, galaxy cluster dynamics, and cosmic microwave background observations. Observational astronomy continues advancing with each new technology. The James Webb Space Telescope observes in infrared with unprecedented sensitivity and resolution. Future missions will observe in wavelengths and with capabilities beyond current instruments. Each advancement reveals new details about galactic structure and evolution. The point here is that physical travel is not necessary for detailed knowledge. We understand the galactic center's structure, the spiral arms configuration, the stellar halo's properties, and the dark matter distribution, all through remote observation. We know the galaxy's rotation period, its total mass, its star formation rate, and countless other properties without having sent probes more than a tiny fraction of the distance across it. This demonstrates the power of observation combined with theoretical understanding. Light carries information about its source. Wavelength distribution reveals temperature and composition. Intensity indicates luminosity and distance. Polarization shows magnetic field. Orientation, temporal variations indicate orbital motion or pulsation. By analyzing light in detail, astronomers extract information about objects without visiting them. The relationship between observer and observed raises philosophical questions. We study the galaxy from within it, part of the system we're trying to understand. Our observations come from a specific location with specific limitations. Yet we've managed to construct accurate models of the whole structure through this limited perspective. This parallels challenges in other domains. Neuroscientists study the brain using the brain itself. Humans trying to understand human nature are themselves human, lacking external perspective. Yet progress occurs in these self-referential investigations, suggesting that internal observation can reveal accurate understanding even without external viewpoint. Consciousness as an observer adds another dimension. The galaxy exists regardless of observation, following physical laws that operated long before conscious observers evolved. Yet understanding of the galaxy requires consciousness to interpret observations, construct models, and derive meaning from data. The galaxy becomes known through the emergence of consciousness within it. Some philosophical traditions emphasize the observer's role in creating reality or meaning. While the galaxy's physical existence doesn't depend on observation, its meaning and significance arise through conscious engagement with it. The same structure appears differently to different observers, to a photon, to a star, to a human, to a hypothetical artificial intelligence. Each perspective reveals different aspects or interpretations. Scientific observation aims for objectivity, describing what exists independent of observer preferences or interpretations. Yet the questions we ask, the instruments we build, and the theories we develop all reflect human consciousness and priorities. A different form of intelligence might study the galaxy quite differently, emphasizing aspects we ignore and vice versa. The value of understanding without visiting raises questions about goals of exploration. If knowledge is the primary goal, observation provides more efficient path than physical travel for cosmic distances. Telescopes reveal details about distant galaxies billions of light years away, regions we could never reach physically. The knowledge gained through observation enables understanding that would be impossible to achieve through travel alone. This doesn't invalidate the drive to explore physically. Direct experience differs from remote observation, providing different kinds of knowledge and different relationships to what's observed. Climbing a mountain differs from viewing it through a telescope, even though the telescope might reveal features invisible from up close. Both approaches have value and provide different perspectives. For the galaxy, the combination of observation and theory has created understanding, approaching what might be achieved through physical exploration while requiring far less resources and time. We cannot travel to the galactic center, but we can observe it in multiple wavelengths, study its properties, and understand its role in galactic dynamics. This knowledge shapes our cosmic perspective, even though we'll likely never visit most of what we study. Future observations will continue refining understanding. New telescopes will reveal fainter objects, probe greater distances, and observe wavelengths inaccessible to current instruments. Computer models will incorporate more physics, achieving better accuracy. The picture of our galaxy will become increasingly detailed and comprehensive through observation rather than travel. The observer's role in a bounded universe becomes clearer. We cannot physically explore beyond limited regions, but we can observe and understand far more. Consciousness enables knowledge that transcends physical presence, allowing appreciation and understanding of the cosmos at scales far beyond what we can reach. This capacity for understanding represents something remarkable, perhaps even unique in the universe. Matter that has become capable of contemplating the structure within which it exists. Living within limits requires philosophical adjustment. The recognition that galactic boundaries create real constraints on possible futures might prompt resistance, acceptance, or various positions between these extremes. Human psychology often struggles with limitation. Much of our cultural narrative emphasizes growth, expansion, and overcoming obstacles. Technological development tends toward increasing capability and reduced constraints. This pattern shapes expectations that limitations should be temporary, subject to eventual circumvention through sufficient advancement. Yet some limitations appear fundamental rather than temporary. The speed of light represents such a limit according to current physics. No amount of technological advancement circumvents it, because it's built into the structure of space-time itself. Accepting this doesn't require abandoning innovation, but rather directing it toward what's actually achievable within the constraint. Galactic boundaries created by distance, gravity, and expansion might represent similar fundamental limitations. Perhaps future physics will reveal ways around them, methods of travel we cannot currently imagine. Or perhaps the limitations will prove as fundamental as the light speed barrier, constraining all possible futures regardless of technological development. Working within constraints characterizes all human endeavor. Engineers design bridges that must operate within strength limitations of available materials and gravitational forces. Artists create within constraints of medium, materials, and human perception. Scientists investigate nature within constraints of measurement, precision, and theoretical frameworks. Constraints don't prevent achievement, but rather define the context within which achievement occurs. The Stoic philosophers of ancient Greece and Rome developed extensive thought about living within constraints. Epictetus distinguished between what lies within our control and what doesn't, arguing that wisdom involves focusing effort on the former while accepting the latter. Marcus Aurelius emphasized working with nature rather than against it, finding peace through alignment with reality rather than struggle against it. These philosophies don't advocate passivity, but rather intelligent action directed toward achievable goals. Instead of frustration at impossible goals, focus on possible ones. Instead of struggling against unchangeable reality, work skillfully within it. The attitude combines acceptance of what cannot be changed with active engagement with what can be. Eastern philosophical traditions offer related perspectives. Buddhist philosophy emphasizes accepting impermanence and limitation as fundamental aspects of existence rather than problems to be solved. Taoist thought advocates flowing with natural patterns rather than imposing contrary will. These traditions developed in different contexts, but address similar questions about human relationship to constraints and limits. Modern existentialism approached limits differently, but arrived at related conclusions. Heidegger emphasized that human existence is always situated, always occurring within specific contexts and limitations. Sartre argued that freedom exists within constraints, that limits create the context within which meaningful choice becomes possible. Camus explored how humans create meaning in a universe that offers no inherent meaning, suggesting that limitation itself provides the framework for meaning creation. Applied to cosmic boundaries, these perspectives suggest several possible responses. We might acknowledge the limitations while fully engaging with possibilities that exist within them. We might find meaning precisely in working within bounded, rather than infinite space. We might develop deeper relationship to accessible regions, rather than superficial engagement with dreams of unlimited expansion. The psychological research on satisfaction and well-being provides relevant insights. Studies consistently show that happiness correlates more strongly with realistic goal setting and achievement than with ambitious goals that remain perpetually unattained. The hedonic treadmill phenomenon demonstrates that constantly expanding goals doesn't create lasting satisfaction. Acceptance and engagement with actual circumstances tends to produce better psychological outcomes than perpetual striving toward unattainable ideals. This doesn't argue against ambition or achievement, but rather for directing them realistically. Within the local group, ambitious goals remain available for millions of years of pursuit. expanding to nearby stars, developing space habitats, understanding galactic processes in detail, perhaps encountering other intelligences. All these remain possible within our accessible cosmic neighborhood. The scope exceeds what any civilization could achieve over plausible timescales. The difference lies in accepting that some things remain beyond reach, regardless of effort. Visiting the Virgo cluster appears impossible, given expansion rates and distances involved. Exploring distant galaxy clusters certainly seems impossible. Accepting these impossibilities doesn't limit what we actually can achieve, but rather clarifies where effort productively directs. Creating meaning within finitude has characterized human experience throughout history. Individual lifespans are finite, yet people find meaning in lives knowing they will end. Civilizations are finite, rising and falling over centuries or millennia, yet people contribute to civilizations knowing they won't last forever. Finite contexts don't prevent meaning, but rather provide the structure within which meaning emerges. The same might apply at cosmic scale. A civilization developing within the local group, accepting this as permanent home, might create meaning through careful stewardship of accessible regions, thorough exploration of reachable systems, and deep understanding of galactic context. The finitude creates focus and priority rather than limitation in any diminishing sense. Religious and spiritual traditions often grapple with finitude and meaning. Many traditions emphasize acceptance of human limitations while maintaining dignity and purpose. The recognition that we cannot do everything, cannot know everything, cannot go everywhere, doesn't diminish value, but rather clarifies it. We create significance through what we actually do within actual constraints, rather than through imagined futures without limits. Secular humanism arrives at similar conclusions through different reasoning. Human flourishing occurs within the reality we actually inhabit, rather than imagined ideal circumstances. Working to improve conditions, expanding knowledge, reducing suffering, increasing capability, all these remain valuable within finitude. The fact that ultimate limits exist doesn't negate the value of proximate achievements. Long-term thinking helps put galactic boundaries in perspective. Over the next 1,000 years, humanity might establish presence in our solar system and begin reaching nearby stars. Over the next 1,000,000 years, we might expand throughout accessible galactic regions. Over the next 1,000,000,000 years, we might thoroughly explore the local group. These timescales vastly exceed historical experience, but remain within the bounds of physical possibility. Beyond these timescales, predictions become increasingly uncertain. Will humanity or its descendants still exist in recognizable form 1,000,000,000 years from now? Will consciousness persist in some form? Will values and goals resemble anything current humans would recognize? The uncertainty itself suggests that worrying about limits on billion-year timescales may be premature. Accepting finitude might ultimately prove liberating. It clarifies what's actually achievable, eliminates anxiety about impossible goals, and focuses attention on meaningful work within realistic scope, instead of dissatisfaction that we cannot explore the entire universe. We might find satisfaction in exploring our actual cosmic neighborhood thoroughly and well. The galaxy becomes home, not through limitation, but through relationship. We exist within it, emerge from its processes, are made of its material, and will continue within it for as long as we persist. This relationship creates connection and belonging that transcends the question of whether we could theoretically leave. The galaxy is home because it's where we are and where we will be, not because we cannot depart, but because we need not seek elsewhere for scope sufficient to any imaginable future. permanence creates different psychological contexts than temporary circumstances. If galactic boundaries represent temporary limitations, subject to eventual circumvention, we might approach them one way. If they represent permanent features of our cosmic context, the approach differs. Current physics suggests these boundaries are likely permanent. The speed of light appears to be a fundamental constant. Gravity functions according to well-tested laws that show no evidence of exceptions. The expansion of space follows from the structure of space-time itself. While future physics might reveal new understanding, the possibility of revolutionary change decreases as evidence accumulates confirming existing frameworks. General relativity has been tested extensively across a wide range of conditions, from Earth-based experiments to observations of binary pulsars to detection of gravitational waves. Each test confirms the theory's predictions to remarkable precision. This doesn't prove the theory will never be superseded, but it does suggest that any future theory must reproduce these confirmed predictions while adding new ones. The basic framework appears solid. Similarly, quantum mechanics has been tested through countless experiments and technological applications. The uncertainty principle, wave-particle duality, and other quantum phenomena aren't quirks subject to technological circumvention, but rather fundamental aspects of nature at small scales. Technologies like semiconductors, lasers, and MRI machines function precisely because quantum mechanics accurately describes reality. The combination of these well-tested theories creates the framework within which galactic boundaries exist. Faster-than-light travel would require violation or circumvention of relativity. Escaping gravitational fields requires energy in amounts determined by well-tested gravitational theory. The expansion of space follows from the same framework that explains gravitational waves and black holes. This suggests the boundaries we face aren't temporary technical limitations awaiting clever solutions, but rather permanent features arising from the structure of physical law itself. This permanence creates a different relationship to the boundaries than if they were merely current obstacles. Consider the difference in how we might approach a temporary versus a permanent limitation. A locked door is a temporary obstacle. Given time and tools, it can be opened or removed. A wall built of laws of thermodynamics, preventing creation of perpetual motion machines or perfect heat engines, represents permanent limitation that no engineering advancement will circumvent. The appropriate responses differ markedly. For temporary limitations, directing effort toward overcoming them makes sense. Research, development, and innovation might eventually succeed. For permanent limitations, such effort becomes futile. Better to accept the limitation and direct energy toward working within it rather than against it. The cosmic boundaries we face appear more like the thermodynamic ones than the locked door. They arise from fundamental aspects of physical law rather than current technical capability. Accepting this doesn't require abandoning scientific investigation. Physics might still reveal new phenomena or principles, but it does suggest that expecting future technology to enable easy galactic escape is unrealistic. Permanence of cosmic context shapes long-term planning differently than temporary circumstances. If the local group represents our permanent home, then decisions about development, resource use, and environmental stewardship take on different weight. There's no future elsewhere if we mismanage what's accessible. The accessible universe represents all we'll ever have access to, making its preservation and thoughtful development crucial. Galactic timescales add another dimension to permanence. Our Sun will remain stable for about 5 billion more years before expanding into a red giant. The galaxy will continue rotating for trillions of years. These timescales exceed biological evolution, civilizational duration, and nearly any other process relevant to human concerns. The galaxy provides a stable framework across time periods that make human history seem instantaneous. This stability creates an enduring context for whatever future unfolds. Political systems rise and fall. Technologies develop and become obsolete. Cultures transform beyond recognition. But the galaxy continues its rotation. Stars follow their orbits, and physical laws operate consistently. This permanence provides foundation beneath the flux of human affairs. The merger of the Milky Way and Andromeda in roughly 4 billion years represents one of the few major changes to our galactic context over relevant timescales. Computer simulations suggest this collision will create a large elliptical galaxy, disrupting current disk structures but creating new configurations. Stars will mostly pass between each other without direct collisions due to vast distances, but gravitational interactions will reshape orbits and trigger new star formation. By the time this merger occurs, Earth will likely be uninhabitable due to solar evolution. The Sun's increasing luminosity will eventually create runaway greenhouse effects, boiling away the oceans. But life or civilization might persist elsewhere in the solar system or on planets around other stars. Those future observers will witness galactic merger from the inside, seeing the sky transform over millions of years as the two systems interpenetrate and combine. Even this dramatic event doesn't change the basic situation regarding cosmic boundaries. The merged galaxy will still be gravitationally bound, still within the local group, still subject to the same expansion that isolates it from more distant structures. The configuration changes, but the fundamental constraints remain. Looking farther ahead, to timescales of hundreds of billions or trillions of years, the galaxy's stellar population will age and eventually cease forming new stars. As available gas is consumed or expelled, the universe will continue expanding, cooling, and becoming increasingly empty as matter spreads ever more thinly across ever greater volumes. But these changes occur on timescales so vast as to be nearly meaningless from any current perspective. The permanence of our cosmic situation suggests that understanding and accepting it benefits long-term thinking. We exist in a specific galaxy within a specific structure of reality. This won't change through technological advancement or future discoveries. The galaxy is our permanent home, and the sooner this becomes part of our cosmic worldview, the more clearly we can plan and act. Peace with permanence differs from resignation. Resignation carries connotations of defeat or unwilling acceptance. Peace suggests integration and harmony, working with rather than against what exists. The Serenity Prayer's wisdom, accepting what cannot be changed while working to change what can, applies at cosmic scales as readily as personal ones. Within permanent galactic context, impermanent human concerns continue. Individual lives span decades. Projects span years to centuries. Even civilizations might persist only thousands or millions of years. All of these unfold within the permanent framework of galactic structure and physical law. The permanence provides stability within which change occurs. This relationship between permanent context and impermanent activity characterizes existence at all scales. Atoms exist within permanent quantum mechanical laws, while participating in temporary molecular bonds. Stars exist within permanent gravitational dynamics, while progressing through temporary evolutionary stages. Humans exist within permanent biological constraints, while living temporary individual lives. Each level shows the same pattern of permanent framework, allowing temporary variation. The galaxy's permanence as our home creates similar structure at cosmic scale. The framework remains stable. Within it, temporary developments, explorations, and transformations occur. The stability enables rather than prevents change, providing foundation for whatever unfolds within its bounds. Understanding permanence might ultimately reduce anxiety about cosmic limitations. If boundaries are temporary, their existence creates tension. We work against them, seeking to overcome them. If boundaries are permanent, they become part of the background reality, no more troubling than gravity or thermodynamics. We work within them naturally, no longer struggling against fundamental reality. The quiet permanence of our galactic context continues regardless of human response to it. The galaxy rotates, stars orbit, gravity pulls, expansion proceeds. These processes operated for billions of years before humans evolved and will continue for billions more after we've either evolved into something else or ceased to exist. The permanence transcends human timescales while providing the stable framework within which our temporary existence unfolds. As we near the end of our exploration, we can reflect on the themes that have emerged. The galaxy's scale creates effective confinement through the relationship between distance, velocity, and time. Gravity extends influence far beyond visible boundaries. Expansion isolates distant structures. Yet these constraints don't diminish what's achievable within accessible regions. Understanding our bounded cosmic context clarifies realistic goals while maintaining appreciation for genuine accomplishments already achieved. We began by asking whether humanity could ever escape the Milky Way. After exploring distance, speed, gravity, expansion, and numerous related topics, we can now address this question more completely. The straightforward answer is no. Humanity almost certainly cannot escape the Milky Way in any practical sense. The distances involved require millions of years of travel time, even at optimistic speeds approaching significant fractions of light speed. The energy requirements exceed anything remotely achievable with current or foreseeable technology. The engineering challenges of maintaining spacecraft systems over such timescales appear insurmountable. But this simple answer deserves qualification. Physical laws don't absolutely prohibit galactic escape. A spacecraft accelerated to sufficient velocity could, in principle, reach escape velocity from the galaxy's gravitational field. Continued acceleration could overcome the pull from dark matter halos. Given enough time and energy, departure is theoretically possible. The impossibility is practical rather than absolute. We cannot maintain spacecraft for millions of years. We cannot generate and sustain the energies required. We cannot shield against cumulative degradation over galactic crossing timescales. We likely cannot maintain human biological or social continuity over the required durations. The accumulated challenges make the endeavor effectively impossible, even though no single physical law prohibits it. This distinction between theoretical possibility and practical impossibility matters for understanding our cosmic situation. We're not imprisoned by absolute barriers, but rather constrained by the extreme difficulty of overcoming accumulated challenges. This creates a different relationship to the limitations than if physical law flatly prohibited departure. The question itself perhaps contains assumptions worth examining. Why would we want to escape the galaxy? What would be achieved by doing so? The accessible universe within the local group contains more stars, more planets, more resources than humanity could utilize over any imaginable timescale. Andromeda alone offers 1 trillion stars to explore. Leaving this abundance to seek additional galaxies beyond reach makes little practical sense. Perhaps the question reflects a more general human drive to explore, to expand, to test limits. This drive has served our species well, leading to geographical exploration of Earth, development of technology, and expansion of knowledge. But the same drive, when directed toward physically impossible goals, becomes counterproductive. Better to direct it toward ambitious but achievable objectives within realistic scope. The accessible universe provides ample scope for such ambition. Reaching nearby stars represents an enormous challenge requiring centuries of development, but appears theoretically achievable. Establishing self-sustaining habitats in space pushes engineering capabilities but violates no physical laws. Expanding throughout the local group over millions of years exceeds current capability, but not imaginable future advancement. These goals, while extremely ambitious, differ from galactic escape in remaining within the realm of physical possibility. They require advancement in propulsion, life support, energy generation, and numerous other areas, but nothing requiring violation or circumvention of well-established physical laws. The difference between extremely difficult and effectively impossible matters for realistic goal setting. Uncertainty remains appropriate regarding very long-term futures. Physics advances continuously, occasionally revealing phenomena or principles not anticipated by earlier frameworks. While major revisions to relativity and quantum mechanics appear unlikely given their extensive experimental confirmation, new physics might emerge at the intersections of these theories or in currently unexplored regimes. Quantum gravity, the currently unknown theory, combining general relativity and quantum mechanics, might reveal new possibilities. Perhaps manipulation of space-time at quantum scales could enable travel mechanisms not currently imaginable. Perhaps vacuum energy could be harnessed in ways that bypass current limitations. Such speculation remains in the realm of wishful thinking rather than plausible expectation, but absolute certainty about future physics would be unwarranted. Still, responsible planning requires working with current physics understanding, rather than assuming revolutionary changes that might never occur. We know relativity and quantum mechanics work across tested regimes. We know the speed of light is constant. We know gravity operates according to general relativity across scales from solar system to cosmological. These facts provide reliable foundation for understanding cosmic limitations, even while acknowledging that future discoveries might modify the picture. The question of galactic escape ultimately connects to larger questions about humanity's cosmic future. Will we expand beyond Earth? Will we reach other stars? Will we survive long enough to attempt such ventures? Will we choose to pursue them? These questions involve technology, politics, economics, philosophy, and human values in complex combinations. Perhaps future humanity, or its descendants, will be content within the solar system, finding satisfaction in development here rather than seeking expansion elsewhere. Perhaps they'll pursue aggressive expansion throughout the local group, establishing presence around as many stars as possible. Perhaps they'll pursue neither, having evolved values and priorities incomprehensible to current humans. The inability to escape the galaxy doesn't determine these futures, but rather constrains their scope. Whatever path is chosen unfolds within galactic boundaries. The local group represents our permanent cosmic home within which all these possible futures develop. Understanding this clarifies context without determining specific outcomes. Accepting boundaries might enable different relationship to cosmic context. Rather than seeing the galaxy as a prison to escape, we might see it as home to appreciate and care for. Rather than frustration at limitations, we might find satisfaction in working skillfully within them. Rather than constant striving toward impossible goals, we might direct energy toward ambitious but achievable objectives. The cosmos asks nothing of us. It imposes no requirements, offers no judgments. Physical laws simply operate according to their nature. How we respond to the reality these laws create remains a human choice, reflecting human values and priorities. Yet our responses matter deeply for shaping individual and collective futures. Whether we accept cosmic boundaries or struggle against them, whether we find meaning within finitude or seek it elsewhere, whether we develop connection to galactic home or remain psychologically rootless, these choices shape experience and outcomes in significant ways. The Milky Way will remain our home. This seems as certain as any long-term prediction can be given current physics understanding. Within this home, vast possibilities remain. Billions of stars await study and perhaps visitation. Countless planets orbit those stars. Resources exist in quantities far exceeding any foreseeable need. The scope of potential achievement within galactic boundaries vastly exceeds anything accomplished so far in human history. Understanding our cosmic context provides clarity for future planning and present meaning-making. We exist in a specific place, within a specific structure operating according to specific physical laws. This isn't a tragedy or limitation, but simply the nature of reality as we've discovered it through careful observation and analysis. The band of light stretching across dark skies connects us visually to our galactic context. Those millions of stars, too distant to distinguish individually with the naked eye, are our cosmic neighbors, fellow members of the Milky Way system. Understanding this connects local experience to cosmic structure in ways that enrich both. We cannot escape the galaxy, but perhaps we need not wish to. Within it, wonders await discovery, challenges invite solutions, and possibilities stretch across timescales that dwarf human civilization. The galaxy provides home, context, and scope sufficient for any achievable future, while remaining the enduring framework within which whatever comes next will unfold.